Hi there, my name is Dimitri and I'm very happy to welcome you to this course on numerical methods. Now before we get our hands dirty on actually applying numerical methods, I want to talk a little bit about who made the course and what the course contains, that sort of thing. So first of all, the authors, my name is Dimitri, as I mentioned. I'm a quantitative analyst and a programmer. I do stuff related to applications of technology in automated trading and quantitative finance, that sort of thing. But for this course, I had some help, so all the narration, all the actual content was made by me. However, all the content was prepared by Xenia, who has been very helpful in getting the actual content for this course. So it is entirely a joint effort, this one. Now, this course is designed for mathematicians, computer scientists, engineers, and basically anyone who needs a numerical solution to some problem. It really doesn't matter what kind of field you work in. So you work in civil engineering, for example, or you are an electrician, whatever the case, you can still apply some of the numerical methods presented here to solve particular problems. So what kind of problems are we talking about? Well, for example, if you look at the integral of log of x between some two bounds, then sure, you can go into MATLAB and we know the analytic solution for an integral of a log. We know what it is. But let's imagine you're stuck with a calculator, or let's imagine you want the calculation done very quickly. Well, in this case, what you can do is you can just plug in a few values. So you can take the lower, the upper bound, and the middle point. You can multiply it by some magic value. And as a result, you'll end up with something that looks like this. So you have a result to 6 decimal places. Now, if we were to actually sneak a peek at the actual value in MATLAB, then you'll see that the value given by MATLAB and the value that we got is only different at the 6th decimal place. But the advantage of our approach in applying numerical methods is that this is something you can do on a calculator which has the log function, whereas for the absolutely precise result we had to use a computer algebra system. Another example is an integral which doesn't have an analytic solution. So for example, an integral of 1 over the square root of 1 plus x squared is not something you can describe in analytic format. So numerical methods are the only thing that you've actually got to sort of find the actual value. And similarly for this equation, x equals e to the minus x, once again, this isn't something that we can simply solve analytically, but applying numerical methods we can find out what the result is, at least to some degree of precision. And final example, let's suppose you're solving an equation ax equals b, where A is some large matrix. Let's say you have a 100 by 100 matrix. Now computers are capable of solving such equations. The only problem is that the amount of calculations that need to be done in order to solve something like this is actually detrimental to the final result, because in doing lots of calculations you lose a lot of precision, and as a result you may end up with an answer which is really far away from what the actual answer happens to be. And once again, this is where numerical methods are applied to give us better answers and to give us those answers faster. So let's talk about what's actually in this course. First of all, we're going to talk about the machine representation of numbers. Let's not kid ourselves. Everything that we do is done on the computer, and computers have limited capacity for storing numbers and for operating on numbers. So we need to be aware of what the computer actually does to a number once we type it in, because remember that if you type in something like 0.1, the computer doesn't really store 0.1. Indeed, it cannot store 0.1. So that's something that you need to be aware of first of all. Then we're going to talk about a couple of kind of important theorems and findings in numerical methods. Just a couple of concepts that we need to keep in mind and apply later on. So these are things like Bolzano's theorem, for example, very common stuff that we're going to be using throughout the course. And then we jump into the meat of the matter. So we're going to talk about one-point iterative methods, two-point iterative methods. We're going to talk about interpolation and curve fitting, and then we'll talk about numerical methods applied to differentiation and integration, the so-called quadrature. So this is what you're going to see in this course. So let's jump in. In order to be able to talk about numerical methods and to be able to discuss things like whether we're losing precision, for example, we need to talk about the way that computers actually store numbers. And for this, we first of all need to talk about the base 2 representation. Now, this is fairly basic computer science, so if you already know this stuff, then feel free to skip forward. But let's actually talk about the numbers that are used in our daily life, which are decimal numbers. So let's suppose you have a number like 60,724.3125. Essentially, this number here is a combination of powers of 10. So you can think of the positions right next to the dot being multiplied by 10 to the power of something. So this would be 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4. And similarly, everything in the fractional part would be 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, and 10 to the minus 4. So what this means is we can take this number and we can actually represent this as a sum. So this is actually 6 by 10 to the power of 4 plus, well, there is no 10 to the power of 3s, plus 7 times 10 squared, that's 100, plus 2 times 10 to the 1, plus 4 times 10 to the 0, plus 3 times 10 to the minus 1, and so on, and you get the other terms as well. So this is base 10 calculation because we have 10 digits that we're using to represent any possible number. Now computers, they have zeros and ones, so every single number has to be represented using base 2. And what this means, since we only have 2 values, is that we have what's called a binary system. So in a binary system, you have a number made up of zeros and ones, which are multiplied not by 10 to the power of something, but multiplied by 2 to the power of something. So a typical number, you might have, for example, 1, 0, 0, 1, 1. Then I'm going to put a point here, and we're going to have some fractional part, 1, 0, 1. So what this would mean is that each of the positions gets multiplied by 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. 2 to the power of 3, 2 to the power of 4. And similarly for the fractional part, that would be 2 to the power of minus 1, 2 to the power of minus 2, 2 to the power of minus 3, and so on. So what you can do, if you want to actually calculate what this binary value is in decimal, you would do a sum once again. So essentially you would say that this is actually equal to 2 to the power of 4 plus, well, these are zeros, we're not taking them, 2 to the power of 1 plus 2 to the power of 0 plus 2 to the minus 1 plus 2 to the minus 3, and you'll get your final value, which is 19.625. All right, so this is what binary generally looks like, and you can consult texts on computer science for how to do conversions from binary to decimal and vice versa. This isn't something that we're particularly interested in. What's important to note, though, is that everything in the whole part and in the fractional part is expressed by a power of 2. An unfortunate consequence of this, as we're going to see later on, is that some numbers are generally very difficult to express. For example, there is no way of expressing 1/3 because you have a finite number of bits in your in the number that's being stored, and therefore you're never going to have a finite representation for 0.3333 all the way to infinity. And similarly, values like 0.1 are also very difficult to express because once again you're limited to powers of 2, and while some numbers, like for example if I had 0.25, that's very easy to express, but 0.1 is extremely difficult, and as a result of this you lose some of the precision. And if you use this number in calculations over and over in some sort of iterative setting, for example, you lose a lot more precision, and this is partly what numerical methods actually deals with. We now need to talk about floating point representation of numbers, which is critical to understanding how computers actually store and operate on numbers. First of all, I want to show you an idea that we'll have to adopt anyway, and this is something that will work in the decimal form as well. The idea is that you only have one significant digit before the dot in any representation of a number, and that is sometimes called scientific notation. So instead of writing 6,519 0.23, for example, what you would do is you would write it so that there is only one digit before the dot, so you would have 6.51923 multiplied by 10 to the power of 3 in this case. And similarly, if you had a very small number, let's say you had 0. And then 5 zeros 391, you would actually change this into 3.91 times 10 to the minus 6. So hopefully the idea is clear, and if you look at, let's say, the calculator that's built into your operating system, you'll see that it has a scientific mode which represents all the numbers in the following format. Okay, so what is it and why does we have to concern ourselves with it when we're talking about floating point representation? Well, the thing is, the computer also wants numbers in this format. So the computer essentially is looking for something like the following. It's looking for a number which has a 1, and then there is a dot here, and then the fractional part, which would be just a bunch of binary values, multiplied by 2 to the power of, and then a few more binary values. And once again, when I write b, that's a bit. So that's either a 0 or a 1. So in this form, we give names to the different parts that we're defining. And those two parts are the mantissa and the exponent. So essentially this part is called the mantissa. And this part is called the exponent. And all the numbers that the computer stores are actually made up of these two parts. But it's not as simple as that. So let's take a look at the way that the computer actually stores this. But before we do, I want to give a brief explanation of how we arrive at the binary representation. How do we actually get any number in the following form? So for example, let's suppose that I have the value of 50. And I want to get it in the form 1 point something something something. What I can do, and this is a bit of a trick, is I can divide it by 2 to the power of something, and then I can multiply it by 2 to the power of that same thing. Now remember that I'm generally looking to have a 1 here in the lead, so I can't divide it by 2 to the power of 100, for example. It doesn't make any sense. But I can divide it, in this case, by 2 to the power of 5, and the reason for that is 2 to the power of 5 is equal to 32. So if I do that, I will get a number which is greater than 1, but on the other hand, I will not get a number that's too small here on the left. So this would be 50 divided by 2 to the power of 5 and then multiply by 2 to the power of 5. Now it might seem like a bit of a pointless exercise, but if you think about this representation, it should make sense to you why we're doing this. Because basically you take this part and you evaluate it, and in decimal form it will be 1.5625. And then the part on the right, so we already know what the exponent is. So this is going to be multiplied by 2 to the power of 5 because that's what we have here. And then we can jump into the binary form. We can represent this value as well as the 5 in terms of bits. So we can say this is actually 1.1001 multiplied by 2 to the power of 101. Okay, so this is a simple example. Let's take a look at another example. Let's suppose you want to represent the value 0.3125. I'm specifically choosing values which have a nice binary representation, but this one is a bit tricky because to get a 1 here, instead of dividing by 2 to the positive power, we have to divide by 2 to the negative power. So in this case, it makes sense for us to divide by 2 to the minus 2, and then multiply by 2 to the minus 2. So this would be in, once again, in base 10, this would be 1.25 multiplied by 2 to the minus 2. Or if we jump to binary, it will be 1.01 multiplied by 2 to the minus 10. And you'll notice that there is a minus here. Now, how can this be? I mean, the computer does not have an ability to store a minus. It can only store ones and zeros. It cannot store this minus here. So we have to deal with this particular situation. And in fact, this is what floating point representation actually does, is it tries to deal with this situation of having negative numbers as well, because numbers can be negative. So how does it do it? Well, essentially, given a chunk of memory, it simply allocates different parts of memory for storing different things. So let's try drawing just a chunk of memory, just an allocation of bits, essentially. All right, so here is a chunk of memory, and we subdivide this memory for various things. And two obvious things that we have to allocate memory for are the mantissa and the exponent. But it's not as simple as that, unfortunately. What we do is we first of all allocate a single bit, so a single 0 or 1 bit, and we allocate it for the sign. The sign. And that's the sign of the number as a whole, which immediately raises the question, well, what about this sign? How come we've forgotten about the sign of the exponent? So we have the sign of the mantissa, but we don't have the sign of the exponent. That doesn't seem to be fair. And I'll explain it in a second. So essentially, whatever we've got left, and that can be, let's say, 63 bits, we can allocate it to the mantissa and the exponent. So we can say, okay, let's subdivide this. So let's have this part as the mantissa. So the mantissa, this can be, let's say, 52 bits. And then for this part, we have the exponent. However, there is no sign bit for the exponent. Instead, what we do is we use something called a bias. And this part, by the way, is 11 bits. So we have 52 plus 11 plus 1, which is equal to 64. So essentially, the mantissa part is fairly obvious. The sign bit is fairly obvious, but the exponent and bias is a bit confusing. So we've currently allocated 11 bits to the exponent. And if we take these values as whole values, then they would be values going from 0 to 2047 inclusive, because that's how many bits we actually have. However, instead of doing this, we need to concern ourselves with this situation, the situation where the exponent can actually be negative. So instead of using this range, we essentially add a bias. So we say that we're going to use a bias value. And in this case, the bias value is somewhere halfway down this range. So the bias value of 1023. So what this means is that instead of having the number represent the exponent exactly, we have this number, the number that's being stored here, and then we add 1023 to it. And this gives us a completely different range of possible exponents, because instead of having the exponents from 0 to 2047, we have exponents from negative 1023 all the way up to 1024. So we have a different range of values, and this range accommodates negative numbers. So that's what we're doing essentially here. Okay, so another little bit of confusion here is that the terminal values, so the value minus 1023 and 1024, are actually used for other things. And those two other things are infinity and not a number. So infinity and not a number. And infinity and not a number are important concepts as well. To kind of simplify the explanation, if you have 1 over 0, that gives you an infinity. Or if you have any kind of number over 0, if you have 2.5 over 0, that gives you an infinity. Of course, if you have minus 1 over 0, that gives you a negative infinity. Negative infinity is also a concept. And whenever you have something like 0 divided by 0, or you have infinity divided by infinity, that's why you get something called not a number. And not a number is a viral thing, meaning that if your calculation has a nan result somewhere and you're using this result, then everything else, all the other calculations involving this nan, are also themselves nans. So it's very important to take care of this if you're doing any kind of calculation which risks dividing by 0, for example. Okay. So now that we're in agreement about how to store numbers, we can actually take a look at how to represent a particular number. And of course, for that, we need to make a decision on how many bits we allocate. For this, there is actually a standard. There is a standard called IEEE 754. And essentially, it mandates two different sizes of floating point numbers. There is single precision and double precision. Single and double. So single precision uses 32 bits and double precision uses 64 bits. So let's suppose that we decide to use the double precision in order to store a particular value. Let's say we want to store the value 22.5. So 22.5. We need to somehow convert it into this notation using all of the things that we've described above. So first of all, we need to normalize the number. Remember, we want one significant bit in front. So essentially, we take 22.5, we divide it by 2 to the power 4, and we multiply it by 2 to the power 4, which gets us 1.40625. 1.40625 multiplied by 2 to the power of 4. Okay, so in double precision, the exponent, we'll take care of the exponent first of all. So the exponent is 4, but let's not forget about the bias. So we say 4 plus the bias is equal to 1027. And 1027 is going to be stored as 1, lots of zeros, and then 1, 1. Okay, so this is essentially our calculation for the exponent. Right, and then the mantissa, which is this part, so the mantissa doesn't actually include the 1. The mantissa is just 0.40625. We don't care about the 1 here because the 1 is essentially implicit. It's part of the number. It's assumed to be part of a number. So this is stored as 0.01101, 000, and then lots of zeros. Okay, so we can now draw the layout of the overall storage of this whole thing. So let's draw it like this. Okay, something like this. Okay, so the sign bit is 0 because that's the sign. Our number is positive, so we don't need the sign. And then here comes the exponent. So let's have the exponent from here to here. So the leading digit of the exponent is a 1. And then we have a bunch of zeros, and then the 2 ones here. 1 here, and 1 here. So this is the storage for 1027. Because 1027 happens to be 1024, which is this bit, plus another 2 plus another 1. So that's 1024 plus 2 plus 1, which is equal to 1027. That's exactly what we get. And then the mantissa, obviously. So that's 0, 1, 1, and then lots of zeros. Okay, so that's the mantissa. All the values here are zeros throughout this whole thing. And then, of course, the assumptions that we've made, of course, is that, once again, there is 1 bit here, and this whole thing, this part is 11 bits, and the rest is 52 bits. And this is how you get a floating point representation of a number. We know that computers have limited capacity for storing numbers, and certainly if you were to compare, let's say, the result of 0.1 plus 0.2, if you were to compare it directly with the result of 0.3, you're in for a surprise, because to us it may appear as though the sum is actually correct. But if you actually do it in MATLAB, so let's do it, 0.1 plus 0.2 equals 0.3, then we get a 0. So why is this happening? Well, the reason why this is happening is because we have only a finite number of bits for representing each of the numbers. And in fact, if you do the following, if we, for example, take 0.1 plus 0.2 and we subtract 0.3, we'll get a non-zero result. We get something like 5.55 times 10 to the power of minus 17. So essentially, there is a problem. We cannot really compare numbers like this, and this applies to pretty much any programming language. Instead, what we have to do is if we want to perform this kind of comparison, we have to rewrite it. We have to say that the absolute value of 0.1 plus 0.2 minus 0.3 is less than some tolerance value. And the tolerance value is strongly related but not equivalent to the idea of a machine epsilon. So essentially, the machine epsilon is a special number that any system will give you, whether it's MATLAB or C++ or something else. In MATLAB, it's EPS. For double precision, it gives us the following value. And what this means, essentially, is that when the numbers are stored in the computer, they're stored with about 16 digits of precision. So if you have a number that's close to 1, for example, it's stored with an error of around 10 to the minus 16, whereas if the number is, let's say, 1000, it will be stored with an error of 10 to the minus 13, and so on. So essentially, the machine epsilon is not equal to this number. So the tolerance here really depends on the kind of calculations that happen inside inside the comparison, inside the functions that you are actually comparing, because the amount of error that can be accumulated through the calculations is really difficult to predict. We do have scientific theory that tells us how we can calculate approximate tolerance values based on the machine epsilon, but in practice what happens is you have super complicated algorithms that you write yourself, and it's simply not possible to use the machine epsilon to predict the overall tolerance, which is why in the real world most of these values, when you see values, tolerance values like this during the comparisons, they're typically experimental. And furthermore, and this is a bit disappointing, you will see differences in tolerance values that you need depending on even the compiler that you're using. Because remember, compilers try to optimize floating point calculations. They have different floating, and as a result, in the real world, the calculation of tolerance values is very much an experimental affair, although strictly speaking, especially for simple examples, you can try to derive actual analytical values, but in reality, we hardly ever do that. So the machine epsilon is certainly available to you, and it does give you an indication of the amount of precision that you're getting when storing numbers. However, it's of very little use when actually comparing the results of calculations. In this recording, we need to talk about the errors which are introduced as a result of using numerical methods. So numerical solutions, they can be very accurate, but in general, they're not exact. And there are two kinds of errors which are introduced when numerical methods are used. They're called round-off errors and truncation errors. So first of all, let's talk about round-off errors. Now let's take a look at a fraction, like 2/3, for example. Now, even if we don't start talking about the computer representation of numbers, then 2/3 is very difficult to describe, even if I were to write it here on this screen, for example, because 2/3 happen to be 0.66666, and all the way, an infinite number of sixes. So the question is, what if I want to write it down on a piece of paper? How would I go about doing that? And in actual fact, there is only two ways that one can go about it. First of all, I can just cut off the number. I can chop it like here, for example, and I can say that 2/3 is approximately 0.66666. That's it. And just have it at that. Or alternatively, I can try and slightly improve the approximation. If we now treat this part as an approximation, I can slightly improve it by doing some rounding. I can say that, well, since this is a 6, I can round it up. I can round this to a 7, like so, for example, and that will maybe give a better representation of the entire fraction when we have just 5 decimal places to work with. So whatever I do, you have to understand that I'm introducing an error here because all of these extra terms are being completely discarded, and as a result, they will not appear in any of the calculations that we do. And as a consequence of that, the final accuracy of those calculations will inevitably suffer. Now, I've done a demonstration here in terms of decimal representation. We have exactly the same problem in the numeric representation of numbers in the computer, because the mantissa, meaning this part, the mantissa is actually finite. It's not infinite. You can't have an infinite number of bits in the mantissa, and as a result, we have to represent numbers to a certain amount of accuracy and simply discard everything that's sort of remaining. So that is the source of the round-off errors. Now let's talk about truncation errors. That's a bit different, because essentially, as we use numerical methods, let's suppose that we used, let's say we have the Taylor series for approximating the sine function. So we want sine of x calculated using the Taylor series, and that's essentially x minus x cubed over 3 plus x to the 5 over 5 factorial, by the way, minus x to the 7 divided by 7 factorial, and so on. So essentially we have this lovely formula which goes on forever once again. And let's suppose that we want to evaluate the value of sine of, let's say, pi over 6. Now, we don't have an ability to plug in this value and get an infinite number of terms calculated, because our existence in this universe is finite, and certainly we want our result as soon as possible. And as a result, we have to make a decision as to how many terms of the Taylor series we're actually going to get. So, for example, let's suppose that I take just the first 2 terms. So I essentially calculate, no, well, let's take just the first term. So for example, my approximation when I use just the first term is that sine of pi over 6 is in fact equal to pi over 6. So a very naive approximation, but essentially this gives me a value of 0.5235988, and so I can calculate the error because I know that the actual value is equal to 1/2, so I can calculate the error, and the error is going to be minus 0.0235988, like so. Okay, alternatively, what I can do is I can take the first two terms, for example. So I can say that sine pi over 6 is now equal to pi over 6. That's the first term here, but also the second term. So that would be minus pi over 6 cubed divided by 3 factorial. So in this case, the error that I will get is going to be a bit smaller. It's actually going to be somewhere around 0.00328. So as you can see, you can take as many terms as you can reasonably compute, but however many terms you get, you will always have the error term. It's just that you can have an error term which is so small that you don't care about it, that you're completely okay with it. Maybe the error term actually goes beyond what is reasonable to store in the mantissa of a double precision floating point number, for example, in which case it doesn't really matter, because even if you had the exact value, there wouldn't be much use for it. There would be no much benefit for it, because you're already getting an error which is so small that it's not going to seriously affect your results. However, this is essentially illustrating the second type of error, which is a truncation error. The fact that however many terms we have in this function expansion, we can never use all of them. And similarly, quite often in numerical algorithms, you'll have an error that's being introduced as part of some sort of iterative calculation. So let's say that the error is rather small when you do it once, but because you have an iterative cycle of some kind, you keep amplifying this error, and eventually it becomes uncomfortable and can even skew your result towards some totally incorrect value. So these are the two types of errors that we're going to encounter as we apply numerical methods. Let's talk about function continuity. What does it mean for a function to be continuous or discontinuous? Well, on the purely intuitive level, what you can think of as a function being continuous or discontinuous is fairly obvious, because essentially if you see a function that's just going like this and doesn't have any breaks or holes or gaps in it, then we can say that the function is continuous. And similarly, if you've got a function which goes kind of like this, for example, and then it continues from this point, then we can say that the function is not continuous or it is discontinuous because there is a gap here. So sometimes we're not interested in the entire function. Sometimes we're interested in, for example, different regions of the function, or for example a specific point, and we want to find out if the function is continuous at this point. So now we can give a formal definition for whether a point, let's begin with points, whether a point is continuous or not. So let's make a definition. So a function f of x is continuous at a point x being equal to a if the following three conditions hold. So the first condition is that f of, sorry, that should be this color, f of a exists. So we need the point to exist, which means that if, for example, you have division by 0 at point A, then that's a problem. That makes the whole thing discontinuous. The second requirement is that the limit when approaching A exists. So the limit as x is approaching A of the function exists. So what this means is that when you approach from the left and you approach from the right, you should get the same value, which is not the case, for example, in this particular point, because here if you approach from the right, you get this value of y, and if you approach from the left, you get this value of y. Therefore, the limit does not exist. And finally, the third condition is that this limit that we have up above, so the limit of the function with x going to a, is equal to f of a. So we really want the limit when we approach from the left and from the right to be equal to the actual function value. So what this means is that the limit is approaching the function from both sides, and it will give us the same result as if we just took the value a and plugged it into the function. So that's what we want. So let's take a look at an example. So for example, let's have a function that looks like this. Let me just draw it. So essentially we have, let's say, have a line going like this, and then we have a line going like this. So at point 2, for example, you can see that the function is continuous because the limits exist. If you approach from the left or from the right, you're going to get the same value. That's the value of the function, therefore everything is correct. However, if you look at this, let's say this is x equals to 6. So if you approach from the right, you get one value of y. If you approach from the left, you get a different value of y. Therefore, the limit does not exist, because the limit exists if the left and right limits are in fact identical. So now let's imagine that you have a function such as, for example, f of x equals to x plus 7 divided by 4 minus x. So what can we say about this function? Is it continuous or not? At what point is the function not continuous? I'm sure you can guess that we have, since the first requirement here is that f of a should exist, we can plug in a value of x such that f of a would not really exist, and that value is x equals to 4. Because if it's x equals to 4, you get division by 0, which is undefined. It gives you infinity. Therefore, the function is discontinuous at x equals to 4. So now that we have a definition for continuity or discontinuity at a particular point, let's talk about the actual ranges. So we might be interested in an interval and whether a function is continuous on an open interval. So for example, the definition, first of all, is that the function is continuous on an open interval from a to b if it is continuous on every point in a and b. So every point in this interval. So let's do another drawing. All right, so let's imagine that we have something like this, and then something like this, and I'm going to give some values here. So let's say this is minus 2, let's say this is 2, this is 4, and this is 6. All right, so this function is continuous on the interval from minus 2 to 2, but it is not continuous on an interval from 2 to 6. So this interval is not continuous, because to be continuous on an interval, you have to be continuous at each and every point, and it's not continuous at the point where x is equal to 4. So finally, if we're interested whether or not the function itself is continuous, then simply instead of taking a and b, we take minus infinity and infinity, and we say, well, is the function continuous at each and every point? So we have this idea of the function being everywhere continuous. Everywhere continuous. So the requirements for everywhere continuous is fairly obvious. You have every point which is actually continuous. So let's give some examples of everywhere continuous functions. So first of all, the power functions. Power functions. So if you have f of x equals x to the n, where n is positive and an integer, then this power function is continuous. So you can think of, for example, x squared, the function x squared, it's everywhere continuous. The second example is exponential functions. Exponential functions. So for example, something like f of x equals 2 to the x. So once again, that would be everywhere continuous. And then another example would be logarithmic functions. So typical example is f of x equals log base 2x, for example. So numerically, what the idea of continuity means is that small variations in the independent variable, meaning the variable that you have here, gives you a small variation in the dependent variable. So that would be f of x or y or something to that effect. Rolle's theorem is actually very simple. So let's suppose that we have a function f of x. Now this function is going to be defined on an interval from a to b, or at least we're going to consider the interval from a to b, and we're going to put the following restrictions. So first of all, we're going to assume that f of x is continuous on the closed interval from a to b. So continuous on a closed interval from a to b. And we're also going to assume that this function is differentiable on an open interval from a to b. Now let's suppose that for this function, f of a is in fact equal to f of b. Now what Rolle's theorem says is that there is such a value c, such that c is somewhere between a and b. So c is a point between a and b, such that the first derivative of the function at this point, when x is equal to c, is in fact equal to 0. So what this essentially implies is as follows. Let's actually draw a picture to kind of illustrate. So let's have the axes going like this, and let's suppose that we have some function or other just going like this. So we can pick 2 points where the value is more or less the same. So for example, we can say that there is a point here and that there is a point here. They both have the same y value, but they obviously have different x values. So that would be a and b. Now what this is saying is that somewhere down the line between a and b, we have a point where the first derivative is 0, meaning that there is a horizontal tangent. And as you can see in our picture, the horizontal tangent to the graph is right about here. I'm not perfect at drawing this, but it's going to be right about here, and there's going to be a point somewhere where this tangent is exactly flat, exactly parallel to the x-axis. So that's basically all that the Rolle's theorem is actually stating, and it doesn't really matter what your function is as long as these particular conditions hold. You're always going to have a point somewhere where this is in fact the case. Even if the function is just a horizontal line, for example, then the first derivative is at 0 at each and every point in actual fact, and the function it can take virtually any shape, and you're going to have at least one point where the first derivative is 0. So as a kind of practical example, if you consider a function, let's have f of x as, for example, 3x squared minus 6x minus 9. So you would have a function that goes something like this. So let me just very crudely draw this one. So it goes like this, and it goes through different points, let's say minus 1 and 3. So what we can say is that at this point, the tangent has 0 slope. In other words, the first derivative of the function is 0. And of course, we can find out that exact point by differentiating the function. So we take the first derivative, and this becomes 6x minus 6. We make that equal to 0, and we get x is equal to 1. So we know that this particular point has an x value of 1. So that's pretty much all that Rolle's theorem is actually stating. The first mean value theorem isn't that difficult either. So once again, we consider a function f of x, and here we only make one requirement. We state that f of x has to be differentiable in some region from a to b. So if we assume that the function is differentiable, then there is such a value c such that the following condition holds. And the condition is as follows. F of b minus f of a is equal to b minus a times the first derivative evaluated at c. And once again, we assume that c is somewhere between a and b. And we can actually rewrite this as a kind of division, so we can have f of b minus f of a being divided by b minus a being equal to f prime of c. So what does this mean? Well, we can look at it in a geometric fashion. So if I just draw the axis lines once again, let's suppose that we have a function going something like this. Okay, so here there is no requirement for a and b to be equal, like we had in Rolle's theorem. Essentially, they can be completely different values. So for example, we can have a being somewhere here, and we can have, let's say, b being somewhere here. So let's have b here. Now what this theorem is essentially stating is that if you draw a line, so if you draw a chord from the points that are pointed to by a and b like so, then somewhere on this interval there is a tangent to the graph which is actually parallel to this chord that we've just drawn. So we can essentially draw it like this. So it's basically saying that whenever you have points A and B, there's always going to be a point which has the same incline as the chord drawn from the appropriate points. Bolzano's theorem is very simple, but we're going to make use of it in our one-point iterative method, so let's talk about it. Essentially, let's imagine that you have a continuous function f of x. And let's imagine that we take 2 points on the x-axis, a and b, such that a is less than b. Bolzano's theorem essentially states that if f of a and f of b have different signs, meaning, for example, f of a is positive, f of b is negative, or f of a is negative, f of b is positive, then the solution to the equation f of x equals 0 lies between a and b, meaning that x is somewhere between a and b. So a very simple way of figuring out why this is visualizing the whole thing. Let's actually draw a simple graph like so. So essentially, let's imagine that you have a function going like this. You take 2 points on it. You take point A and point B. Now, point A gives us a negative f of a. So f of a is negative. And here, the point is actually positive. So here, f of b at this point is positive. So they have a different sign. And because they have a different sign, you can make the assumption that the point where this intersects the x-axis actually lies somewhere in between. Right here, for example. Now the question is, how do you determine whether two things have equal sign? We certainly, in computer programming, we have the signum function, for example. So you would have something like the sign of f of a, and that would give you a 0 if it's positive, and maybe a 1 if it's negative. It depends on the function, actually. But there is a much simpler way, so forget all that. Essentially, you multiply f of a and f of b. So you multiply f of a and f of b. If they have a different sign, the result will be negative, because it will always be negative times positive, which is negative. So f of a times f of b will be negative. Otherwise, for example, if they're both positive, or if they're both negative, the sign will be, the result of the multiplication will be greater than 0. So essentially, all you have to do to make sure that the solution lies between a and b is to multiply f of a by f of b and to check whether it's less than 0. If it's less than 0, then the solution is between a and b. If it's not, then the solution is somewhere else. And that's the gist of Bolzano's theorem, and we're going to make use of it quite a bit later on. Our first port of call when trying to find numerical solutions to equations, for example, would be one-point iterative methods. So that's what we're going to talk about first of all. So let's imagine that I'm trying to solve a simple quadratic equation. Let's have x squared minus 5x plus 2, for example. Now, I'm not going to solve it analytically. I know that we have a formula for solving quadratic equations. Instead, let's suppose that I decide to do a plot. So I draw the graph of the equation, and by equation I mean that I set f of x being equal to x squared minus 5x plus 2. So that's what I have on the y-axis. So I have y equals x squared minus 5x plus 2, and I observe what kind of results I actually get. So if this is a 1, 2, 3, 4, and 5, then I will observe something like the following. I'll have a parabola which goes through some point between 0 and 1, and then up it goes through the point between 4 and 5. I'm not very good at drawing these, but you get the idea. So let's suppose that I have some knowledge about the fact that there are two roots between 0 and 1 and 4 and 5. How can I prove that they are in fact in those regions? One of the ways to prove it is using Bolzano's theorem, which we've talked about already, so we can actually apply it. Just in case you forgot what Bolzano's theorem is all about, essentially it's a claim that if the solution to an equation f of x equals 0 lies between 2 points a and b, then f of a times f of b is actually less than 0. And the argument for this is that we want them to have different signs. So if you take f of 0 here, you would have this point which has a positive y value, whereas f of 1 would be somewhere here. This has a negative y value. Negative times positive equals negative. That's why we check for the product to be less than 0. So in this case, we can verify this. We can plug in the values of 0 and 1. So we would have f of 0, and that's actually equal to 2. We would have f of 1, that's actually equal to minus 2. And so f of 0 times f of 1 equals 2 multiplied by minus 2, which is minus 4, which is less than 0, which satisfies our criteria. It satisfies the criteria we've outlined here. And so by Bolzano's theorem, we know that there is a root somewhere between 0 and 1. And you could do the same with the values of 4 and 5. Now, in one-point iterative methods, what we're going to try to do is we're going to try to rearrange the original equation such that we have an x on the left-hand side. So let's remind ourselves, first of all, what the equation actually is. We have x squared minus 5x plus 2 being equal to 0. What I'm going to do is I'm going to take this x and I'll have it on the left-hand side of the equation, and I'll simply rearrange everything on the right-hand side. And after I do that, I end up with x being x squared plus 2 and divided by 5. So essentially, this rearrangement can give us an iterative scheme. It can give us a scheme which yields new and updated values of x as we kind of plug them into the equation. So essentially, we can rewrite this in the following form. We can say that x at the iteration k plus 1 is evaluated given the value of x at iteration k squared plus 2 divided by 5. And this should explain why we have the actual name of our topic as one-point iterative methods, because essentially what's happening here is you only have a single point in the iteration. You have this point xk. There is only one piece of information that's actually being taken to produce the successive estimates. So that's why we call it a single point iterative method. So how do we apply this method? Well, it's actually really easy. First of all, you have to take an initial guess value. You have to say, for example, let's suppose that I take the initial guess to be equal to 1. And what I do is I take the value of 1 and I essentially plug it into this recursive formula. So I plug it into xk. I get 1 squared plus 2 divided by 5. That's 3 over 5, or 0.6. So my second guess at the solution is equal to 0.6. Now I can decide what kind of precision I actually want from this method. So for example, let's suppose that I'm interested in 5 decimal places. So as soon as I have no change in the 5th decimal place, I can start this iterative scheme. And by the way, this should be an x1. So as I keep plugging these values into the iteration scheme, I end up with the following set of values. So I have x2 being equal to 0.472, and I plug a few more values in here, and somewhere down the line I may get the value x7 being equal to 0.43845, and then I do this once again, and I have x8 also being 0.43845. 5, and you notice that these two values are the same, so they're the same to 5 decimal places, and as a result I can essentially state that this is my result. I'm satisfied with the result which doesn't change at the 5th decimal place. This is what is called a fixed point. In the iteration. So essentially a fixed point is just the root of the equation. Although in this case we're basically saying that since we're interested in a particular precision, that's really all that we want. We want 5 decimal places and we are not interested in going beyond that. So we take this value and we say that it's good enough for our purposes. Now the amount of calculations that you have to do really depends on the starting point. It depends on the x0 that you've chosen, and I could have chosen a completely different value. So for example, if I had chosen x0, for example, to be 1.2, which, well, let's have 1.2, yes, this actually happens to be outside the range of values, because we know the root is somewhere between 0 and 1. This cannot possibly be the root. But in any case, I would get the value of x1 being equal to 0.688, and somewhere down the line, I would get x9 being equal to 0.3845. So you'll see it took one more step than it did for the better, shall we say, guess. And in both of these cases, we're lucky because the iteration scheme, the scheme that we've set up here, the iteration scheme actually happens to converge to our actual value. And this is not always the case. It's not always the case that your iteration will converge at all. For example, let's suppose if you have something like 3x squared minus 2x minus 2 equals 0, you can, first of all, we know that there is a root between 1 and 2 because f of 1 is equal to minus 1, f of 2 is equal to 6. There is a difference of sign here, so we know that there is a root somewhere between 1 and 2. We can rewrite this formula, rearrange it so that we just divide everything by 2 and then take the x out. So we get x equals 1.5 x squared minus 1, or if we use the k subscript notation, that would be x with subscript k plus 1 equals 1.5 times x k squared, and then we can once again start plugging in the value. So if we assume that the root is between 1 and 2, we can take the value of 1.5 as the initial guess. So we say x of 0 is 1.5, but then something strange happens because we calculate x with index 1, and that's equal to 2.375. We calculate x2, and that's 7.461. We calculate x3, and then we get the value of 82.498, and so on. So you can see that we're never going to converge to the actual root. So iterations will never converge, and in mathematical terms, we can say that x of k happens to go to infinity as k goes to infinity. So essentially, we're never going to get our actual value, and that's something to watch out for when applying single-point iterative methods. In order to illustrate convergence, we're going to look at a very simple example. So I'm going to have two lines, two graphs plotted here. So one of them is going to be y equals x, so the line that's kind of going at a 45-degree angle. So this is y equals x, and then the other line is going to be some function that we're interested in. So I'm going to just call it f of x. So y equals f of x. All right, so what we're interested in is finding the intersection point, the point where the x-axis and the y value, the x value and the y value are kind of identical. And in order to do this, we're going to start with an initial guess. So we're going to say that, well, what about, for example, this value? What if this particular value, let's call it actually x0, what if this value happens to be the right value? And what we do then is we draw a line from this point to the point on the actual graph, so we get to see whether our result is in fact correct. So we end up here and we see that obviously the x and y coordinates are not the same. The y coordinate is much greater than the x. So what we do then is we draw a horizontal line from this point towards the point y equals x. And so we draw a kind of horizontal line in this direction, and we end up somewhere here. Okay, so now that we end up on this point, and we can call it x1, by the way. So this particular point is going to be called x1. So at this particular point, what we do is we once again draw a vertical line towards the curve. So we draw a vertical line towards y equals f of x. We end up at this particular point. And so what we do afterwards is we continue the process. So we go left back to the line, we go back up to this line, to the right, to the right, to the right, and eventually we converge to the point that we're actually interested in. So this is a simple illustration of convergence. Effectively, we converge to the point that we were actually looking for. However, this approach does not always work. In some cases, you might have the same kind of setup, but it simply will not work. So let's take a look at an example of that, a different kind of plot. So once again, we're going to have y equals x going like this, y equals x, and then we're going to have some function that goes like this. So we're going to have this function y equals f of x. And now let's suppose that we once again adopt this approach of picking some point x0. And you'll notice that in actual fact, what's happening here is if we want to find out the point of an intersection, which is actually somewhere at the origin, we're not going to get it. Because what happens as we pick some initial value x0, we go up towards the function, we go right towards the line y equals x, then we go orthogonally once again towards the function, we go right towards y equals x, we go up to well, almost infinity, and we're never going to get the result, which is that they intersect somewhere near the origin. So in this case, what we're looking at is divergence. We're looking at a situation where there is no convergence, and that's what's called divergence. So this method actually converges if in the neighborhood of the intersection point the derivative has an absolute value that's smaller than 1. So let's write this down and let's take a look at an example of that. So we have this requirement that for the function f of x, we're going to converge if the derivative of this function has an absolute value less than 1. If this is the case, then it's going to converge. So for example, let's suppose that we have f of x being equal to 2 divided by e to the x plus 1. So the first derivative of that, f prime of x, is equal to minus 2 e to the x divided by e to the x plus 1 squared. Okay, so let's draw this. Let's have the y and x axes, so the line going like this a bit, and let's suppose that y equals x is still what we're interested in. So we're interested in this particular point, and we might have different guesses as to our initial guess. So we might have x being equal to 1 and x being equal to 3. These are the two guesses. So let's take a look at the first derivative at x equals 1 and at x equals 3. So the first derivative at x being equal to 1 is equal to minus 2e divided by e plus 1 squared. So that would be about minus 0.39. So that's certainly less than 1 in magnitude. On the other hand, the first derivative at x equals 3, which is equal to minus 2e cubed divided by e cubed plus 1 squared, is also within that limit. It's actually much smaller. It's about minus 0.09. So essentially, in this case, what's happening is we are satisfying this condition. We are satisfying the condition that the first derivative is smaller than 1. So the values that are being provided, and the approach that we take will actually be convergent and will actually find our intersection point. And of course we can draw the diagram with any of the starting values. So I'm going to choose a different color. If I start at the value of 1, I'm going to get here, then here, then here, then here, and you can see that it eventually gets right to the point where we need to be. And similarly, if I start outside, if I start at 3, what will happen is I go up here, then I go left here, and then it's the same as the green path, and we're going to converge. I think we can all agree that we want our sequences to converge faster, and we would do pretty much anything to actually get that. So as a result, let's talk about the acceleration of convergence. How can we actually get our sequences to converge faster? So let's suppose that we have our sequence xn with n going from 0 to infinity, and it converges to some value L. So let's imagine that this is a linearly convergent sequence. What we're going to consider first is something called Aitken's delta squared process. So this is actually worth writing, Aitken's delta squared. And the idea here is as follows. Essentially, we formulate a new process that supposedly converges faster. So we're going to have a new sequence which is going to be x star n, with once again n going from 0 to infinity. And x star n here is defined as follows. We define it as x n plus 2 minus the following fraction. So at the top we have x n plus 2 minus x n plus 1 squared, and at the bottom we have x n plus 2 minus 2x n plus 1 plus xn. So we now have a new process to consider. So let's take a look at an example. So let's suppose that we have a sequence where xn is equal to the cosine of 2 over n plus 1. Now this sequence converges linearly to a value of 2. So let's try to determine the first 5 terms, for example, of the sequence given by the delta squared process. And in order to do this, in order to determine a particular x star n term, because that's what we're actually after, we need to have the terms xn, xn plus 1, and xn plus 2 as well. So we actually have to determine the first 7 if we're interested in the first 5 terms of x star. We need to determine a whole 7 terms of xn. So let me briefly plot the actual values here. Okay, so just from looking at this, you can see that x star n certainly appears to be converging faster to the value of 2 than xn, and that's actually what we wanted. Now what we can do is we can apply a modification of Aitken's delta squared to a linear convergent sequence that's obtained from a fixed point iteration, and we can accelerate the convergence to quadratic, and this procedure is known as Stephenson's method. So Stephenson's method is somewhat different from Aitken's delta squared because to find a solution to some equation in the form x equals f of x, for example, given some initial estimate x of 0, we compute the following. So we compute x1 as f of x0, and we compute x2 as f of x1. And then for each subsequent term, we compute xi plus 3 as xi minus, and here we have xi plus 1 minus xi squared divided by xi plus 2 minus 2 xi plus 1 and plus xi. Alright, so without Aitken's delta squared process, Stephenson's process looks like this. So to find a solution of f of x equals 0, for example, you start by choosing some point xi as the first estimate, and then the subsequent estimates are computed by the following formula. So the subsequent estimate xi plus 1 is equal to xi minus, and then on top we have f of xi squared divided by f of xi plus f of xi, like this, minus f of xi. So let's actually take a look at how this is done in MATLAB. Okay, so here is a definition of Stephenson's root, and what we're doing is we're essentially trying through 100 iterations, and you can certainly change this number, and we're trying to get the appropriate result and looking at some tolerance. So we have a tolerance value for the kind of error that we might actually get. So let's take a look at how this would actually work. Let's do format long, and then I'm going to define a function f, a function of x being x minus 2 times e to the minus x, for example. And now let's suppose that I want to find the root of this function. So that would be Stephenson root with passing in the function itself as well as the initial guess, let's say a value of 1, and here is the final result. We're now going to introduce another concept called the order of convergence. So let's imagine that we have a sequence of n elements. Let's call it xn, with n going from 0 to infinity. And going from 0 to infinity, and let's suppose that this sequence actually converges to some value L, with xn not being equal to L for all n. Now we can introduce two positive constants, let's call them alpha and mu, and then formulate the following relation. So we can say that the limit with n going to infinity of the absolute value of x n plus 1 minus L divided by x n minus L to the power of alpha is equal to mu. So what we're saying essentially is that the sequence converges to L, and the order of convergence is this alpha. So alpha is the order of convergence, and mu is some asymptotic constant. Asymptotic constant. All right, so we have, let's say we have some iterative technique for finding the value of x. So we have x n equals some function g of x n minus 1. And we can say that this iterative technique is of order alpha if the sequence actually converges to the solution of order alpha as outlined above. Now in general, a sequence with a high order of convergence will actually converge more rapidly than a sequence of a lower order. And the asymptotic constant that's here on the right basically affects the speed of convergence, but not to the extent that the order does. Now two cases of the order of convergence should be given special attention. So first of all, if we have a situation where alpha is equal to 1 and mu is less than 1, then the sequence is linearly convergent. Linearly convergent. And the second case that we need to mention is alpha being equal to 2. In this case, the sequence is quadratically convergent. Quadratically convergent. So essentially, if you think about a fixed point iteration algorithm, this has linear convergence. And on the other hand, something like Newton's algorithm, for example, has quadratic convergence. So let's take a look at an example of what the calculations would be for linear convergence and quadratic convergence. Just some sample numbers to get a feel for what you're getting, essentially. So as you can see from the illustration, the quadratically convergent sequence is within 10 to the minus 89 of 0 by 7 terms, whereas to achieve this kind of accuracy with linear convergence, you would have to have at least 126 terms to achieve a similar result. Newton's method, also known as Newton-Raphson, is a very popular numerical scheme for finding a solution to the equation f of x equals 0. And we're going to take a look at how exactly this works. So the requirement for this method to actually work is that the function f of x has to be continuous and differentiable. But once it is, we can actually do quite a lot in terms of finding the root. So let's do a plot. I'm trying to do nicer plots for once. Okay, so here's the idea. Let's suppose that we have a function that goes something like this. So it goes whoop, like this. So this is f of x. And somewhere down here is the root that we're trying to find out. However, let's suppose that our initial guess isn't so well educated. Let's suppose that we're actually quite far away. We're sort of up here. So our initial guess is x0. So here's the idea of Newton's algorithm. Basically, what you do is, first of all, you compute the function at the initial guess. So the y-coordinate of this particular point would be f of x0. And then what you do is you plot a tangent. So you consider a line that's tangential to the graph. It could go something like this, for example. And you consider this tangent and you consider where it intersects the actual x-axis. And that's going to be your second guess. So your second guess, which is x1, is going to be here. And once again, you compute the value of the function at f of x1 now. And you perform roughly the same thing. So once again, you do a tangent. You end up at a point x2. And eventually, sooner or later, you're going to end up at a point which is either at the root or very close to the root. So you might have some guess x3, for example. And this is pretty much the gist of Newton's method. So essentially, if we were to formulate this symbolically, we would say that the iteration xi plus 1 is actually computed based on xi minus the value of the function at xi divided by the first derivative, once again at xi. I'm sure you can see where the first derivative comes from. The tangent to the line happens to be the first derivative. So this is essentially an iteration formula, because the solution is found by repeated application of this equation for each subsequent value of I. So let's take a look at a very simple example. So let's suppose that we're trying to solve the equation 1 over 2x minus 1 equals 0. Now we know we can solve this analytically. We know that x is actually equal to 1/2, but let's suppose that we want to try and find this numerically. So once again, if we do a quick plot of the function, let's do a quick plot. So essentially it's going to go something like this, and essentially that's our f of x here. So we're going to start with, once again, an initial guess. And this time, if let's say this is a 0.1 and this is a 0.2, we're going to start with some guess, which is, let's say, 0.2. So we say initial guess is 0.2. And then for a numerical solution, for the solution using Newton-Raphson, remember we need the first derivative as well. So we need to take this function 1 over 2x minus 1 and we need to differentiate it. So the first derivative of this function happens to be minus 1 over 2x squared. Okay, so we now have all the parts we need to apply Newton's method. So essentially we can formulate the expression for x at n, or let's do I, x at I plus 1. And we're going to formulate it as xi minus f of xi divided by f prime of xi. That's Newton's method, and now we perform the substitution. So essentially for the function, so we have xi minus, and then the function of xi, that's this whole thing essentially. So that would be 1 over 2xi minus 1 as the numerator, and then the denominator is the first derivative, so that would be minus 1 over 2x squared. And after we simplify this a little bit, we get xi plus 2xi squared multiplied by 1 over 2xi minus 1. And just factoring out the xi, we can say that this is essentially 2 times xi minus xi squared. Okay, so we now have an expression, an iterative expression for the subsequent term, and what we can do is we can actually start plugging in these values. So first of all, we're going to plug in our initial guess, which is 0.2. So we're going to say that x1 is equal to 2 times, and then here is what we need to plug in. So that's going to be 0.2 minus 0.2 squared, and that's going to be about 0.32. Now our subsequent guess, x2, is going to be 2 times this guess, 0.32, minus 0.32 squared, which is equal to 0.4352. And then let's do another guess, x3, and this guess is going to be 2 times 0.4352 minus 0.4352 squared, and that's going to be roughly 0.4916, which is very close to the actual value of 1/2 that we know is the actual answer. So here it is. In just 3 iterations, we managed to get to within 1/100th of the actual value, and that's fairly quick, and that's why the Newton's method is actually so popular. Alright, let's take a look at the Newton-Raphson implementation in MATLAB. Now it's actually very simple because all I have here is a function which takes some function f and its first derivative, and it applies the Newton's method for the number of iterations that we specify with the initial guess that we specify. So let's actually try feeding it some data. So first of all, we're going to have the function itself, and that's going to be 1 over 2 times x minus 1, just like we had in the example we just did. And we're also going to have g defined as a function of x, which is going to be that first derivative. So that was minus 1 divided by 2 times x squared, like so. So that's g. And now what we can do is we can call simple Newton's method, and we can call it with f, g. We're going to specify an initial guess of 0.2 as well as 3 iterations, and here is what we get, 0.4916, just like we had in the example. And we can certainly increase the number of guesses. If I increase it to 10, for example, you're going to see that we get a perfect 0.5. Alright, so far we looked at the use of Newton's method in solving very simple kind of problems, like a kind of f of x equals 0 problem. Now we're going to take a look at using Newton's method for slightly more complicated kind of problems. So we're going to consider a system of nonlinear equations now. So let's suppose that we have the following equations. We have y minus 0.2 times e to the 0.2x plus e to the minus 0.2x equal to 0. And the second equation is going to be x squared plus 4y squared minus 16 equals 0. So that's an elliptic equation. Now we're going to give these both of these parts of the equation, both of the left-hand sides, they're going to be essentially vector valued functions. So we're going to say that f1, which takes an x and a y, is going to be defined as the following, and we're going to have the second function f2 of x and y defined as this. So let's actually draw this on a graph and see what we're actually trying to find out. So here is an improvised graph with the x and y axis. Now the second equation is something like an ellipsis, so it goes something like this. Obviously it's symmetrical, I'm not that good at drawing. And then the other equation, the first equation, would go through something like this. And what we're really interested in is this point here. We're interested in the point of intersection. We want to find out its x and y coordinates using, once again, Newton's method. So in order to apply Newton's method, what do we need? Well, first of all, we need a couple of guesses as to where this point is. So for example, I can say that x of 0 is going to be equal to 3 and y of 0 is going to be equal to 0.5. These are our starting positions, and these are the positions we're going to start from. Now remember that in this simple example, in the example of Newton's method for f of x equals 0, we had to take a first derivative. Well, now unfortunately both of our functions, f1 and f2, they're actually vector valued functions. And as a result, if we want to formulate some sort of statement with regard to their derivatives, it's not a simple case of differentiating. We're going to have partial derivatives, and we're actually going to build something called a Jacobian matrix. So this Jacobian matrix requires the partial derivatives of the function f1 and f2 with respect to either of the arguments. So we have to have 4 partial derivatives in total. So let's compute df1 by dx, and that's going to be equal to 0.04 multiplied by e to the minus, actually no, that's not a minus, multiplied by e to the 0.2x minus e to the minus 0.2x, and we're going to have the partial of f1 with respect to y. That's just going to be equal to 1 because here is the only y-related term and its derivative is 1. And then the partials with respect to f2, first of all, df2 by dx, that's going to be equal to 2x because the only term with x is the x squared here. And then the partial with respect to actually these should be 2's, so partial df2 by dy, that's going to be equal to 8y because once again this is the only term that contains the y. So now we have the 1, 2, 3, 4 partials, and we can build a Jacobian matrix out of them and calculate the determinant. So essentially what we're interested in is we're interested in the determinant, the Jacobian determinant for functions f1 and f2, and this is the determinant of the 2 by 2 matrix composed of their partials. So that's df1 by dx, df1 by dy, df2 by dx, and df2 by dy, like so. So we can now plug in those values that we have because we've calculated all 4 of them. So this will be the determinant of the following. So df1 by dx is this long thing, so that's 0.04 times e to the 0.2x minus e to the minus 0.2x, like so. Then df1 by dy is a 1. The term here will be 2x, and this will be 8y. And after you calculate the determinant, so this times this minus 2x, we're going to get the following. So we're going to have 0.32y multiplied by e to the 0.2x minus e to the minus 0.2x, and this all minus 2x. So this is the Jacobian determinant. And now what we need to do is we need to find the delta x and delta y. So we need to essentially calculate the displacement, if you will. So delta x here is going to be defined as a rather long fraction. So I'm going to draw a rather long line here to accommodate it. So this is going to be minus f1 at a point x0, y0 multiplied by df2 by dy, once again at a point x0, y0, plus f2 at a point x0, y0 multiplied by del f1, there's a 1 in here, by dy, once again at a point x0, y0. Managed to run out of space. Okay, and down below, we're going to divide it by the Jacobian. So that's going to be the Jacobian of f1 of x0, y0, and f2 of x0, and y0. Like so. So if we plug in the actual values, we're going to get something like the following. We'll get minus 0.0258 times 4 minus 6, all divided by minus 5.7963. And that's roughly 1.053. And then we do the same for delta y. So let me move this up, and we're going to have delta y being defined. I'll do a longer line this time, knowing that we need lots of space. So this is going to be minus f2 at a point x0 and y0 times del f1 by dx at a point x0, y0 plus f1 at a point x0, y0 times the partial of f2 with respect to x, once again at a point x0, y0, all divided by the Jacobian at f1 of x0, y0 and f2 of x0, y0. So once again, we plug in the values and we get something like the following. Let's draw another line here. So we get 6.0, actually no, it's 6 times 0.0509 plus 0.0258 multiplied by 6 divided by minus 5.7963. So what we end up with is a value roughly equal to minus 0.0794. So now that we have the delta x and delta y, we can calculate the x and y values using the following terms. So essentially we define x1, the next iteration in our guessing for the actual x value, as x0 plus delta x. So that's going to be equal to 4.053. And then y1, which is defined as y0 plus delta y, is equal to 0.4206. So obviously the values of x1 and x2, or rather x1 and y1, which are obtained here, are not the true solution. Nonetheless, these values are expected to be closer to the solution than our initial guess, x0, y0. So the solution process actually continues by then using x1 and y1 as the new estimates for the solution and determining new sets of delta x and delta y's that give x2 and y2. And these iterations, they continue until two successive answers differ only by an amount smaller than some desired epsilon value. Let's take a look at the implementation of multidimensional Newton's method in MATLAB. Then there is plenty of code here, so I'm going to take it slow in explaining what's going on. First of all, we're defining our functions f1 and f2, and then what we're doing is we're using the symbolic toolbox to actually differentiate these functions against x and y, so we're getting the first derivatives for the first and second function. Now what's happening afterwards is we're getting the Jacobian, and the way that it works is we get the determinant in symbolic form, but then we're using a function called MATLAB function. Now what this function does is it basically turns a symbolic calculation into a function which takes a bunch of values, because we cannot directly invoke the determinant as a function. So we have to call this MATLAB function thing. And MATLAB function is actually not that great because it takes only the arguments which you actually have defined as symbolic variables. So for the determinant, we know that x and y are pretty much going to be there, but if you were to evaluate some of these derivatives, you'll get a constant, for example, and that would lead you to have a function with no arguments. So for having the functions of the first derivatives, what I'm doing instead is rather complicated. I'm basically taking the symbolic evaluations that we've had, I am substituting the arguments, so basically I'm having functions take x, and y. I'm substituting those instead of x and y, and then I'm calling the eval function to actually give us a numeric value, because otherwise you'll end up with fractional values and whatnot, and this isn't great. So it's a bit roundabout way of defining these functions, but once you've defined them, what we're doing is we're defining the initial guesses. So the initial guess, 10 and 0.5, and we're defining the error tolerance that we're generally happy with. And afterwards, we perform the actual calculation. So we get the Jacobian first of all, then we get the delta values. We calculate the x and y values that we've got from this method, and then we compare them against the actual values. So we're essentially looking at the error. We're looking at how much the result has changed over the last iteration. We print this out, and if the error is smaller than the tolerance value we specify, then we simply stop executing by invoking the break. So let's actually run this. As you can see, even though we asked for 5 iterations, and that's exactly what we've got. And you can see the error here. It's slowly going down with each number of iterations. So this is how you use multidimensional Newton's method. In our previous example, we used multidimensional Newton's method, but in many instances, it's actually not possible or not very efficient to find a closed formula for the Jacobian matrix, which is what we actually need to use Newton's method. So in these particular cases, what we can turn to instead is finite difference approximations. So we can actually estimate each of the entries in the Jacobian matrix, and the resulting method is called approximate Newton's method. So here's the idea. Let's suppose that the Jacobian entries have indices I and j, and what this means is that we're talking about partials in the following form. So that's going to be dfi by dxj. I'm using x for every single dependent variable here. So essentially what we want to do is we want to estimate these partial derivatives using a finite difference approximation. So that would be something like this. We define dfi by dxj as some delta j times fi. So we want to actually have a delta multiplier to the function. So essentially, and I should be doing an approximate sign here. Essentially what we're saying is we'll do a finite difference. So we'll say that this is fi at point xj plus h minus f at xj. There we go. And this is all going to be divided by h, where h is obviously some small number. Okay, so let's do the example that we had in the previous session, the example with the two functions, one of them being an ellipsis. Let's do it once again. So just to remind you what we had. So f1 of x and y was defined as y minus 0.2 times e to the 0.2x plus e to the minus 0.2x, like so, and that was equal to 0. And then the other function, f2 of x and y, was defined as x squared plus 4y squared minus 16, also equal to 0. So once again, we're looking for the intersection point, and we have some starting coordinates. So just like last time, the starting guess is that x of 0 is equal to 3, and y of 0 is equal to 0.5. Okay, so armed with this and the knowledge of finite differences, we can actually try and get our deltas. So delta, first of all, we're going to have delta 1, so 1, f1, that's going to be the following. And once again, we're going to have a fairly long fraction. So I'm going to draw a very big line here. Okay, so that's going to be fi at xj plus h minus f at xj, all divided by h. So that if we plug in f1, first of all, that's going to be something like the following. So it would be minus 0.2 times e to the 0.2. And here we have x plus h plus e to the minus 0.2 x plus h. So all of this plus 0.2 times the original f at xj, so that would be e to the 0.2x plus e to the minus 0.2x. And all of this is divided by h. So we can collect the terms a little bit. We can take out the 0.2. So that's going to be 0.2, and I'm going to draw another line just as big almost. So that's going to be 0.2 multiplied by e to the 0.2x plus e to the minus 0.2x minus e to the 0.2 x plus h minus e to the minus 0.2 x plus h, all divided by h. So we got an expression for delta 1 f1. Now we want an expression for all the other parts, because remember the Jacobian has 4 terms. So this was df1 to dx, and this was df1 again to dy, and this was df2, same here. So we need 4 terms, and we only got 1 of them. So let's do the other ones. So the other ones are going to be a bit easier. So delta to f1 is quite simply y plus h minus y divided by h, so that's equal to 1. Now, why is it this particular amount? Let's take a look at what's actually happening. So for the second delta, we're actually using the index 2 here. So the index 2 here is essentially the index of x2 in our notation, but because we have a function of x and y, essentially what happens, these x and y, they map onto x1 and x2. So essentially all that's happening when we talk about x2 is we're getting the y value. So that's why we get y plus h minus y divided by the h, and that's equal to 1. And the other values are equally easy. So delta 1 f2 is equal to x plus h squared minus x squared divided by h. And then delta 2 f2 is equal to 4 times y plus h squared. I should probably move this out the way because it's kind of overlapping what we're doing here. I'll do it a little bit lower. So that's 4 times y plus h squared minus 4y squared, all divided by h. So now we have all the 4 delta times f products. And now we can actually express the determinant. So we can calculate delta f, the actual equivalent of the Jacobian. So this is the determinant of the following. So that would be delta 1 f1, delta 2 f1, delta 1 f2, and delta 2 f2. And this is where we plug in everything that we've written so far. So that's going to be a rather large thing. And I don't really want to sort of copy over this particular bit. So I'll just call it sigma for lack of a better word. And I'll copy the other ones though. So we'll have sigma, here we'll have a 1, here we'll have x plus h squared minus x squared divided by h, and here we'll have 4x plus, that's y, 4y plus h squared minus 4y squared, all divided by h. So we need to calculate the determinant of that, and that's going to take quite a bit of time. I'm not going to show the workings here because sigma is really large. Let's just assume that we'll keep the function somewhere. Actually, why not? Let's write it out. So it's going to be 0.8 multiplied by e to the 0.2x plus e to the minus 0.2x minus e to the 0.2x plus h minus e to the minus 0.2x plus h. So that's this part, and then all of this gets multiplied by the following. So we have y plus h squared minus y squared. So this is divided by, I better do a nice line if I'm going to draw this. This is all divided by h squared, and subtract from that x plus h squared minus x squared divided by h. So this is essentially the determinant. So it's this sigma thing times this bit minus this part multiplied by 1. So here it is. Okay, so now that we have an expression for the overall delta here, what we can do is we can choose some tolerance, we can choose some h value that we're happy with, and use that as a kind of finite difference. So for example, we can say, let's have h being equal to 10 to the minus 6. So now, armed with this value, what we can do is we can calculate delta x and delta y, and that's what we need for the actual iterations. So first of all, we'll calculate delta x, and delta x is essentially the idea of taking the values, the delta values, and plugging them in. So this would be essentially defined as the following. Once again, a very big fraction coming up. So that would be minus f1 at x0, y0 multiplied, and remember we had the partial derivatives here at a particular point. Well, not anymore. This time we replace it completely, and we replace it by the product of the delta, in this case delta 2, and the function f2 at y0. Plus, and we'll have the function f2 at x0, y0 times delta 2 f1 at y0, all divided by delta f at x0, y0. So after we substitute the values, we end up with 0.9838. And then the same goes for the delta y. So delta y in this case, and we had the formula before, once again, big line here, that's essentially minus f2 at x0, y0 times delta 1 f1 x0 plus f1 x0 y0 times delta 1 f2 at x0, all divided by delta f x0 y0, and that's equal to roughly 0.0243. So we now have the values of delta x and delta y, and afterwards we just repeat the process as we did before. So essentially we say that we have a new estimate for x1, a new estimate for x, which is x1, which is x0 plus delta x, and we calculated delta x up above. So that's essentially, remember x0 was 3, so the x1 is 3.9838. And similarly for y1, that's y0 plus delta y, and that's equal to this value plus 1/2, so that's 0.05243. Actually, I put an extra 0 in here. Let's have it like this, 0.5243. And then, of course, what you do is if you want refinements of x1 and x1 and y1, then you plug in the values once again. You go through the entire process and you keep iterating until you get until the change becomes sufficiently small that you are happy with the result. Alright, so here we go again with calculations in MATLAB, and this time you're not going to find any differentiation in here, because essentially, apart from defining the functions themselves, as we did previously, all we're defining the initial guesses for the x and the y. We're defining some sort of error tolerance that we're happy with at some point at which we're going to stop, and then we perform a certain number of iterations. Now the h value is defined as 10 to the minus 6, and we're prepared to iterate 5 times in order to find the new values. So here are the finite difference calculations for d1, f1, d2, f2, and so on, and then we plug those to calculate the actual determinant. So this is the Jacobian from the finite differences. Then we calculate delta x and delta y. We calculate the new guesses for x and y, and then we look at how much they've changed, and if the change is less than what we wanted, which in this case is 0.01, then we stop. So as I run this, you'll see that in just 3 iterations, we managed to satisfy the error requirement, and we also got our actual results. Horner's algorithm for polynomial equations is actually a very simple affair. But to discuss it, let's actually take a look at an example. Because let's suppose you want to evaluate something simple, like let's say you want to evaluate ax squared plus bx plus c, for example. So if we talk about how many operations are required to actually compute this, we can write it like so: a times x plus b times x plus c. So essentially we have three multiplications. 1, 2, 3. So we have three multiplications and we have two additions. But this isn't the most efficient way of going about it, because we can make it more efficient. We can factor out the x and have x times ax plus b plus c, or if I write this out, let's put a dots in here, then once again we can count the number of operations, so we can have this time two multiplications. So just two multiplications and two additions. I'm going to circle the additions, so that's two additions. So essentially, if we optimize the evaluation of the polynomial, we end up with a situation where for a polynomial of degree n, and in this case n is equal to 2, so for a polynomial of degree n, Horner's algorithm for polynomial equations requires just n multiplications and n additions. So let's now formalize Horner's algorithm. So the way to do this is, first of all, let's discuss what we're actually trying to find out, because essentially what we're trying to do is we're trying to evaluate the polynomial at a particular point. Let's call it x0. And this is something that you would use, for example, if you were doing Newton's method to locate the approximate zeros of a polynomial, you would need to be evaluating lots of these polynomials at different points. Not just the polynomials, of course, in the sense of the polynomial of the function, but also the first derivative at some particular point as well. So Horner's algorithm basically goes something like this. So you have a formal definition for the polynomial, which is an x to the n plus a n minus 1 x to the n minus 1, and all the way down to a2x squared plus a1x plus a0. So this is a polynomial in Horner's form, and now what we want to do is we want to leverage this kind of factoring out, and we want to formalize it. So the way to formalize it is as follows. We define a new sequence. Essentially this, we can think of this, the a coefficients as a sequence of a's going from 0 to n, where n is the order of the polynomial. We can now define a new sequence called b, and we define it as follows. So the last term bn is actually equal to an, or the first term, depending on whether you read it from right to left or from left to right. So the order, the highest term actually stays the same, but the next term, which is bn minus 1, is actually defined as a n minus 1 plus bn x0, where x0 is the point at which you're attempting to actually evaluate the polynomial. And so for some point bi with an index I, this would have the value ai plus b at I plus 1 x0. And then all the way down to b0, which would have the value a0 plus b1 x0. So this is the way of formalizing the evaluation. And now let's take a look at an actual example. So let's suppose that we have a polynomial p of x, which is equal to 3x to the 4 plus, let's have minus here, minus 2x squared plus 2x minus 4. So I missed out the x to the cubed, and that's okay. So we want to evaluate this polynomial at a point x of 0 equals minus 2. So the way we do this, using the formula that we talked about up above, is we do this kind of table. So essentially we know the starting point x of 0 is equal to minus 2. And then we collect the coefficients of each of the terms. So essentially we want the coefficient of x to the fourth, and then the same goes for x cubed, x squared, x, and the constant term as well. So the coefficient of x4 is equal to 3, the coefficient of x cubed is minus 2. Oh no, actually there is no x cubed. There is no x cubed. The coefficient is 0. The coefficient of x squared is minus 2. The coefficient of x is 2. And the constant is equal to minus 4. And now what we do is we calculate those b values. So remember, the b value is just, well, the first b value here, the one at b4, happens to be this coefficient, because the coefficient of bn is the coefficient of an. And I suppose we should be explicit here that this is a4, this is a3, this is a2, this is a1, and this is a0. Okay, so b4 is equal to a4, so that's equal to 3. But for b3, the calculation goes as follows. So essentially, if we look up above, you'll see that b at a value n minus 1 is a at a value n minus 1 plus bn times x0. So this would be equal to 0, a3, plus the product of bn, which is 3, times x0, which is minus 2. 3 times minus 2 is minus 6, so that's minus 6, and the end result is minus 6. Then we move on to the x squared term, and we have b2 here equal to 10. I'll omit the calculations. Then for the x term, we have b1 is equal to minus 18. And finally, the final term b0 is equal to 32. And this happens to be the result that we're looking for, because the final term in the calculation is what's actually the polynomial evaluated at point x0. So that's exactly what we're looking for in the first place. So here is once again an example of the Horner's algorithm for polynomials done in MATLAB. And as you can see, it's very simple. We have a function called Horner alg, and the reason it's alg is because otherwise it would conflict with the Horner function that's already built into MATLAB. So Horner alg takes two things. It takes the x0, the point at which we actually want the evaluation to be done, and in addition it takes a matrix or a vector of the arguments which make up the polynomial. So we can actually try it with the example that we've just done. Essentially what I'm going to do is I'll define the set of polynomials A to have the same polynomial coefficients that we had. So that was 3, 0, minus 2, 2, and minus 4. And then what we can do is we can invoke Horner alg with that set of coefficients plus x0, which in our case was minus 2. And as we run this, we get exactly the same result, 32. A while back, we looked at Bolzano's theorem, and you might be wondering where this theorem is relevant. So the bisection method, which we're going to discuss right now, is exactly the place where Bolzano's theorem applies, because what we're trying to do, once again, is we're attempting to solve the equation f of x equals 0, and let's actually do a plot so that we can see what it's all about. So here is a plot of the y and x axes, and let's suppose that there is some function that goes kind of like this, and we want to find out the intersection, as always. Now, what the bisection method basically says is that we can make an educated guess about the range in which the solution is. So, for example, we can do a plot and we can say, well, if there is a point A here and there is a point B here, such that f of A actually gives us a negative value, as can be seen here. So this is going to be f of A, this location. And similarly, for f of b, we get a positive value somewhere here, so that would be f of b. What we can say is that we know that the solution is between a and b if the sign changes, and that's what Bolzano's theorem was all about. So essentially what we can say that if f of a times f of b is negative, then we know that the solution is somewhere between a and b. So then the bisection method basically says, well, you've got this range, how about dividing the range in half? So we find a middle point, it's called point C. And then we consider the sign change between A and C and the sign change between C and B. And there are two possibilities here. So one of the possibilities is that when we calculate f of A, f of C, this is less than 0. So that's one possibility. The other possibility is that we get f of C, f of B being equal to 0, or less than 0 rather. So if f of A and f of C, if their product is less than 0, that means that the solution is between A and C. If the product is less than 0, f of C, f of B, then we know that the solution is somewhere between C and B, once again leveraging Bolzano's theorem. So in this case, we have f of A times f of C less than 0, because if you look at the picture here, you'll see that this is where the solution lies. So once again, we get a value of f of C. F of C is positive, f of A here is negative, so we know that their product is going to be negative. So we know the solution is between A and C, and once again we do a bisection. So once again we subdivide this range from A to C in half, and we once again, let's call this point D, we once again perform the same consideration. So we look at f of A, f of D, and we look at f of D, f of C. And we say, well, which one of these is negative? So this time round, we can see that f of D, f of C is negative. Because once again, if you look at the actual plot, you'll see that f of D gets negative here, f of D, and f of C is positive. So we choose this particular option, and we continue this onwards, and then onwards, until we get a suitable result. So this is the whole point of the bisection method. All right, let's take a look at an example of the bisection method in MATLAB. So first of all, what I'm going to do is I'm going to take the function that I want to solve for. I'll define it here, and I'll do a function plot of this function on a range from -5 to 5. All right, so here is the actual plot. Let's do a grid so that we can see what's going on. Here we go. Okay, so you can see that if we look at the zeros here, you can see that the 0 is somewhere between, let's say, 2 and 3, more or less. So that's our guesses. So A is 2 and B is 3, and that's what we begin with in terms of trying to find the solution. And we specify the number of iterations that we're prepared to do in order to actually find the root, and we specify some sort of tolerance. Now what we do then is we take a look at f of A and f of B. If their product is greater than 0, then we say that there is a bit of a problem because the function has the same sign. So it doesn't actually, the solution isn't actually between A and B. However, if the product is not greater than 0, then we can actually perform the iterations. And for each of the iterations, we find a midpoint. So here it is, A plus B divided by 2. And we also calculate the actual value of the function at this point. So here is fp. And then there are a couple of options. So one is that we've already found the solution, which would be excellent. But it's also possible that the actual value that we find is either indicating that the solution is to the left or to the right. And depending on this, we actually perform the appropriate assignments. So as you can see, if f of A times fp is less than 0, then we choose B to be the right point. So essentially we're using A and B as left and right. So we're saying the right point is now P, otherwise the left point is now P. And we repeat the whole iteration once again. So as I run this, you'll see that we've done 10 iterations, and we've gone through a couple of values of A, B, and P being the midpoint, and eventually we get to a result where f of P is sufficiently small. So it's 189th millionth the final result. And if we're happy with this result, this is where we actually stop the iteration, or we could continue forever. The regular fallacy method is actually a very old method for finding the solution to an equation in one unknown, and it's similar to the bisection method, but it does take a different approach. So let's take a look at how it works. Once again, we're solving the equation f of x equals 0, and we have knowledge of the solution being on some interval from a to b. So let's once again do a drawing and see what we get. All right, so let's have the y-axis here, and let's have the x-axis going like this, and let's assume that the line that we're interested in, the function, goes something like this. Okay, so if we find 2 points which are sufficiently bracketing the interval, let's say we'll have a here and b here, we can once again calculate f of a, which is going to be around here, f of a, and then f of b at this point, f of b. And in the bisection method, we basically split the distance between a and b halfway, and we went with that. But with the regular fallacy method, we're going to do something different, because instead of doing this, what we're going to do is we're going to draw a line which connects the point a f of a and b f of b, and we're going to draw a line. So I'm going to draw a line like this. And instead of taking the halfway point between a and b, we essentially look at the intersection of this particular line with the x-axis. So remember, we're looking for this point. We're looking for this point, and we're attempting to get closer to it by first of all considering this point, because this is the first point of intersection. So let's call this point C. So once again, we grab this point, we calculate f of c, and then we apply Bolzano's theorem once again. So just like in the previous example, what we're essentially doing is we're looking at whether the sign changes between f of a and f of c, or whether the sign changes between f of c and f of b. And we continue doing this. So for example, we know that the solution is between c and b. Therefore, we once again draw a line between this point and this point. And you'll see that as I draw this line, it gets us closer to the solution, so we get a new point D, and we can once again draw a line, and eventually we'll get to the right solution. So if we were to actually formalize this whole thing in terms of mathematical notation, then we can say that the following. So given the interval from a to b, the equation of a straight line that actually connects the points, let's say point B to f of b, to the point a f of a, is given by the following. So we have y being equal to f of b minus f of a divided by b minus a times x minus b plus f of b. So this equation here is the equation of the line from this point to this point. And then, of course, as we've seen before, we actually apply Bolzano's theorem, meaning that if f of a, f of c is less than 0, this means that the solution is between a and c, and if f of a, f of c is greater than 0, then the solution is between C and B. So there is to it. Now let's take a look at how it's done in MATLAB. Okay, so here's an outline of how we would do this in MATLAB. Once again, we have a function, and it's a similar function to what we had for the bisection method. And then we have the assumption of the range going from 2 to 3, and we have the maximum number of iterations. We once again have the tolerance, and this time around what we're doing is for each of the iteration steps, first of all, we apply this calculation. That's the calculation that we had in the previous demo. So that would be this part. We calculate the y using this particular formula, and then what happens is we look at whether we're hitting the tolerance marker that we are actually interested in, meaning that we are getting the kind of tolerances that we want, and then we simply adjust either a or b depending on the sign of f of a times f of c. So that's pretty much all that it does, and as we run this, you'll see that in just 4 iterations we're getting to within the kind of distance that we're happy with. We're still pursuing this idea of finding a solution for f of x equals 0, and we're going to consider yet another method of finding the solution. And this method is called the second method, and it's actually an approximated form of Newton's method. So let's take a look at an example once again, I'm going to draw how it actually works. So let's have the y-axis and the x-axis going like so, and then let's suppose that here is the function that we're trying to solve for. So we're once again looking for this particular point. So what the second method suggests is that we pick some points. We pick a point x0 and x1, and then we try to connect a second, so a chord, which actually matches those two values. So for example, if I pick x0 to be here, so if I just crudely draw it to roughly this point, and then if I pick, for example, x1 to be somewhere here, so let's have x1 here, right? So we get another point. So then the idea is as follows. You draw a line going through these 2 points. So you draw a line that goes something like this, roughly. I'm not being 100% straight here, but this kind of line. And you have the intersection with the x-axis, so that gives you a new value. That gives you x2. And then you project x2 up, and you get a new point, and then you connect x1 and x2, and that might give you a different kind of point, a point much closer to what we're looking for, and that would be x3, and then you would go up, and you would connect these 2 points, and eventually you'll arrive at the result. Now, it may appear to you as though I've doctored this example so that we would always be going from the right towards this point. So let's take a look at a different realization. Let's draw something more tricky. Okay, so let's have another set of axes. I'll move this up a bit. Okay, so let's imagine that our line goes something like this. So it goes from below, and it goes like this. And let's suppose that our initial choices, so our x0 and x1, are actually on either side of the line. So x1 might be here, x0 rather. x0 might be at this particular point, and then x1 might be at this particular point. So somewhere here. Now what happens when you join these two? When you join these 2 points is you get a line that looks like this. So you get a line that looks like this, and essentially x2 would now be here. So x2 would be here, and then you project down to the line, and then once again you connect this line up with x1, and you might get something like this. So you might get a line that goes through here, and you would have the next point, x3, being somewhere here, and you proceed to repeat the result. So actually the iteration formula is very similar to something that we've seen before. In fact, it's the same formula as for the regular fallacy method. So the iteration, the x value at I plus 1 is equal to xi times f of x I minus 1 minus x at I minus 1 f of xi, all divided by f of x I minus 1 minus f of xi. So this simple formula, you just plug in x0 and x1, and you're going to eventually arrive at a point xn where it's very close to the point that you're actually looking for. So now let's take a look at how to do this in MATLAB. Alright, so here is the implementation of the second method. It's actually very similar to what we had previously for the other single point iterations, but this time round we have the function, we have x0 and x1. Notice the change in terminology. We're no longer talking about a and b. We're not saying that a and b somehow bracket the root. That's not the case. So we have the first 2 guesses. We have the maximum number of iterations. We specify once again the maximum error that we're okay with. And then we go through the iterations. We calculate the new x value. We calculate the y value at this point, and then we look at the tolerance. And once again, if we're happy with the tolerance, we just break and print the value. If we're not happy, then we recalculate the x0 and x1 positions, essentially reusing the variables. We're not making an array of the x's with like x2, x3, whatever. We just reuse x0 and x1 for the bounds, and we run this again. And when I execute this, you'll see that within 4 iterations, we get within an acceptable tolerance level. In this part of the course, we're going to talk about interpolation, and specifically in this clip, we'll talk about polynomial interpolation. But first of all, let's discuss the question of what is interpolation all about. Well, if you sort of roll back to the time when we didn't have computers and calculators and whatnot, and you wanted to find, let's say, the sign of some function, so you wanted sine of x, you basically had a book of tables where you looked up the values. So the book would tell you, for example, that the sine of 0.123 is equal to such and such a value, and the sine of 0.124 is equal in such and such a value, and that was the only way that you could actually get the values of the sine function, apart from somehow trying to calculate this yourself. So the question that was asked is, what if you want to find out the sine of, let's say, 0.1235? Now, this isn't in the table, so instead what you have to do is you have to somehow read between the lines, so to speak, and figure out what the sign of the value is based on some values that you already know. And this is ultimately what interpolation is all about. It's about reading between the lines. So the general idea of interpolation is that if you are looking, if you've got a function of x, like for example sine of x or something, then given a number of points, you might be looking for some other function which also coincides with those points. So it might be, for example, a polynomial, some polynomial of x, which is equal to the function of x at specific points. So essentially you might have a couple of points, let's say x1, x2, x3, and so on up to some xn value, and you already have those points. You know what the function, let's say the sine of x is at those points, and you would be looking for a polynomial which also coincides with these points. So let's take a look at an example. So for example, let's suppose that my f of x is going to be equal to e to the power of minus 1 over x. 1 over x, like so. So essentially what I'm going to have is I'll just have a table of just a few values. Typically you would consider just a couple of values, maybe like 5 or 6. We'll consider 3 values here. So let's suppose I have the values at 1.1, 1.2, and 1.3. So my function f of x, or maybe I'm reading a table somewhere, or maybe I've calculated it myself, I have the values 0.4029, 0.4346, and 0.4634. Okay, so these are the values I have, and let's suppose I am looking for some value that's in between. Maybe it's 1.15 or something else. I want to get a polynomial which actually goes through these 3 points. So how do I get it? Well, if I'm looking for a polynomial p of x, which is defined, let's say we have a second order polynomial, so that would be ax squared plus bx plus c. What I can do is I can take these values of x and I can plug them into the polynomial, and on the right hand side I would be expecting the same values of y as the original function. So essentially what we get out of all of this is we get a system of equations. So we plug in the values and we get a system of equations. So 1.1 squared, for example, is 1.21a plus 1.1b plus c, being equal to the right hand side, so that's 0.4029, and we get similarly the other 2 equations. So we get 1.44a plus 1.2b plus c equal 0.4346, and 1.69a plus 1.3b plus c being equal to 0.4634. And so you solve the system of equations and you get the values of a, b, and c. So you get a equals to minus 0.145. Now, before I continue, I have to say that at this moment, we cannot really assume that there is even a solution to all of this, because the coefficient matrix may as well be singular and we might not get solutions. But in this particular case, because I'm doing this demo, we are lucky. We have a solution, and that solution is as follows. So I've got the value of a, the value of b is equal to 0.6505, and the value of c is equal to minus 0.1372. And we can plug in these values a, b, and c into the polynomial, and what we get is the following. So we get the polynomial of x being equal to minus 0.1455x squared plus 0.6505x, and then minus, it should be a minus, so minus 0.1372. So we essentially have a polynomial which at points 1.1, 1.2, and 1.3 gives us the same result. So if you want the polynomial to be evaluated at a point 1.15, for example, you would simply plug it into the polynomial function here, and you would get an approximate estimate based on this polynomial interpolation. So I just want to show what the end result looks like in MATLAB. All I'm doing here is a plot of the two functions, the e to the minus 1 over x and the polynomial, and I'm plotting them from 0 to 2. So let's run this, let's see what we get. So here we are, let me stretch it a little bit, and as you can see, we're having the blue line is the actual function. So you can see that at x being equal to 0, for example, it's really far away from what the function actually is. But we're only interested in the 3 points which are shown with the x's here, and it looks as though the points more or less coincide, and as a result we can argue that the polynomial evaluated at some in-between point, like here for example, would be approximately equal to the actual function. And that's what interpolation is all about. Now, one thing I wanted to mention is the example that's being shown here is only for illustration. In the real world, you will not be constructing the interpolation polynomials in such a direct manner as to solve a system of equations. That's not something that is typically done. It's especially a bad idea if you have a polynomial of a high degree. The calculation of the interpolating polynomials by using this idea of systems of equations is a bit too complicated, so the Newton basis greatly simplifies the actual approach, and the way it's able to do this is by producing a different notation for the polynomials. We essentially record them in a different fashion. Here is how the polynomial looks. So let's consider for example, a polynomial of the third degree. So we're going to have cubic splines being used to model some function. So polynomial of a third degree with the Newton basis approach is described as follows. It's going to be a set of coefficients. I'll actually no longer call them a, b, and c, and so on. I'll just call them a0, a1, a2, and so on. And a0 is actually going to be the lowest order, so a0 is going to be the constant, a1 is what's going to be in front of the x, a2 is what's going to be in front of x squared, and so on, just to alleviate the confusion. So with the Newton basis, we rewrite the polynomial as follows. We say that it is a0 plus a1 times x minus x0 plus a2 times x minus x0 x minus x1 plus a3 times x minus x0 x minus x1 x minus x2, like so. So this is our new way of writing the polynomial. You'll see that it involves a lot more because essentially now it's directly incorporating not just the constants of multiplication but also some values of the actual function. So how can we use this, and why does it matter? Why does it matter that we have this kind of notation? And the reason is that essentially if you think about this in terms of a matrix, then instead of solving a system of equations, essentially instead of an n by n matrix, it's still an n by n matrix, but it's triangular. So finding the values of a, giving the values of x and f of x is actually really easy. So let's draw a table of some values and we'll try solving this. So let's have a very simple table with a set of x and f of x values. So I'll have some, let's have 4 values because that's what matches the description up above, even though we can extend it to any kind of polynomial. So we'll have the values 0, 1, 3, and 4. You'll notice they don't really have to be contiguous or equally spaced, nothing like that. And then we'll have the function values themselves. Let's have 4, 3, 31, and 84. And now what we can do is we can take each of these values and plug them into the actual function. Because essentially when we talk about x0, x1, x2, and so on, that's these values. So this is essentially x0, this is x1, this is x2, and this is x3. So how can we actually get the coefficients? Well, we take x0 and we start thinking about what will happen if we plug x0 into the Newton basis. So this term has x minus x0. So you plug x0 in here, you plug it literally in place of the x, and this term vanishes because it's x0 minus x0. And of course, it's also repeated here, so it vanishes from here, it vanishes from here, and any further terms, if we had any, would also vanish. So we know that a0 is actually equal to the function. So we may as well write it down. So essentially, in this particular case, we say that a0 is equal to 4 because that's what the function value is. So now what happens with x1? x1 is equal to 1. So we take x1 and we plug it into the whole polynomial. But you'll notice that here we have x minus x1 where x1 is being plugged in. So this term vanishes, this becomes 0, the whole thing becomes 0. This term also vanishes, we only have the first two terms. So we essentially have a0 plus a1 multiplied by x minus x0, and that's x1 minus x0. So that's multiplied by 1 minus x0, and that's equal to 3. So we can rewrite this, of course. We can say that in actual fact, let's wipe this out because it kind of simplifies, and we get simply a0 plus a1 being equal to 3. And from this result, we can immediately deduce that a1 is equal to minus 1. So the third calculation, once again plugging x2, I'm going to omit the workings here and just give you the final result. So we'll have a0 plus 3a1 plus 6a2 being equal to 31. And then the fourth calculation will be a0 plus 4a1 plus 12a2 is equal to 84. So this is easy to solve. You're not solving really a system of equations, because once you have this, you get this automatically, then you get this automatically, and so on and so forth. So it's very quick to solve. And once you actually get these values, what you get is a set of values for the a coefficient. So you get a0 equal to 4, a1 equal to minus 1, a2 being equal to 5, and a3 being equal to 2. And so you take these values and you plug them back into the Newton basis. So essentially you say that P3 of x is actually equal to 4 minus x plus 5x times x minus 1 plus 2x times x minus 1 times x minus 3. And this simplifies to 2x cubed minus 3x squared plus 4. And this example wouldn't be complete without a MATLAB illustration. So once again, I'm here exemplifying what we've just done essentially. So we have the interpolated function, and we also have a bunch of points. And if I run this, you can clearly see that the set of points we were looking for happen to coincide with the polynomial. When we were talking about the Newton form in the previous recording, I was telling you how great it is that you don't have to solve a system of equations because the whole thing is diagonalized. Well, guess what? It gets even better at this point, because we can actually avoid solving any equations whatsoever. We can get our results immediately. And to demonstrate how this actually works, I want to talk about divided differences. Now, it's a more complicated concept in terms of derivation, so please bear with me as I explain how the whole thing goes. Now, remember we had a set of formulae for the overall polynomial, and we can sort of subdivide it into the particular parts which are relevant for the solution, i.e. the value of the function. So, for example, if we're considering let's say linear polynomials, linear interpolation to begin with, then we could have the following definition. We could have f0 being defined as a0, like we had in the previous example. Remember, we got the a0 pretty instantly. And then we have f1 being equal to a0 plus x1 minus x0 multiplied by a1. So that's what we had before. We also had f2, f3, f4, I think. No, actually we had just f2 and f3, but we're going to keep it simple for now, because what we're going to do now is we're going to subtract one from the other. We're going to subtract f0 from f1. And what we'll get is the following. We'll get f1 minus f0 equals x1 minus x0 multiplied by a1. The a0s go when you subtract. So now we can take f1 minus f0, we can divide them by x1 minus x0, and we get the following. We get a1 equals f1 minus f0 divided by x1 minus x0. And so we're going to introduce another form of notation, because this thing that we've just come up with is what's called a first divided difference of the function f. So let's write this down. This is a first divided difference. And we're going to introduce a notation where the f is going to have square brackets and we'll have the terms in there. So here it's x0 and x1. So we can write them down like so, x0 and x1. And as you can imagine, if you were to swap x0 and x1, you will get exactly the same result, because you'll simply get a minus here, and that will cancel out whatever the signs are. So we can say that the divided difference, the first, in fact, divided difference between x0 and x1 is the same as the divided difference between x1 and x0. So this divided difference may appear as an artificial construct, a kind of something that we've just invented, but we're going to stick with it, because now that we've done the linear case, this was the linear case, we're going to add another term. We're going to add the f2 term here and consider the quadratic case. Quadratic. Okay, so the quadratic case would look something like the following. We'll introduce the term f2, and f2 is going to be a0 plus x2 minus x0 plus x2 minus x0, x2 minus x1 multiplied by a2. And I think I forgot an a1 here as well. Okay, so what can we do with this? Well, we can do f2 minus the f1 that we had before. We can take this and subtract from this. So we'll say f2 minus f1. Okay, so this could be tricky. Some terms will actually cancel out. Let's take a look at those terms which will cancel out. So f2 minus f1, the a0s, they cancel out. And also minus x0 times a1 here and minus x0 times a1 here. These things will cancel out, but everything else will remain. So what we'll end up with is the following. We'll end up with x2 minus x1, the x2 comes from here and the x1 comes from here, so x2 minus x1 times a1 plus x2 minus x0, x2 minus x1 multiplied by a2. Okay, so now what we can see from this is we can see that these terms are identical, x2 minus x1, so we may as well divide by them effectively. So we have f2 minus f1 divided by x2 minus x1, and that's being defined as the following. So it's the divided difference. Now, the divided difference, where does it come from? Well, it comes from a1, because remember, a1 is the first divided difference. That's what we came up with as our notation. So f2 minus f1 divided by x2 minus x1 is the first divided difference between x0 and x1 plus x2 minus x0, that's this term times a2. Okay, so now we introduce yet another term, or we're almost ready to introduce yet another term, because we want to extract the a2. So how do we extract a2? Well, we once again rearrange the entire thing. So we essentially have this notation that this particular construct, being the first divided difference between 1 and 2, we'll rewrite this as f with square brackets x1 x2. Okay, and what we do to get the a1 is we take this part. So we take this part, we move it over to this side, and then we divide by x2 minus x0. So a2 is now defined as follows. It's defined as divided difference between x0, x1 minus divided difference. Actually, that should be a1 and a2 here. So the x1, x2 minus this part, so divided difference between x0 and x1, all divided by x2 minus x1. Okay, and once again, we're going to introduce a notation for this divided difference. The notation will be that we'll now have f with square brackets, and we'll have all the three terms. So x0, x1, and x2. x0, x1, x2. And this is going to be the second divided difference. Second divided difference. Okay, right, now we can continue this onwards and we can actually come up with the third divided difference, but we're going to employ a bit of a trick to actually come up with the last one. Now remember that when we're interpolating the polynomial, it really doesn't matter what the order of the points are, because we can shuffle the points around, and because we have this assumption, and I haven't given a proof to this, but I've alluded to the fact that the interpolating polynomial is a unique polynomial, we are in fact to rearrange the position of x0, x1, x2, x3 as we want when we're interpolating it. So for example, for describing a3, which is the next thing that we want, I want to rearrange the points a little bit, so we'll have the points in the following order. We'll have the points as x2, x1, x0, and then x3. And this is a trick that I'm doing because now what I want to do, if you remember in the previous clip, we actually had a third order polynomial, and that's exactly what I want to do. I want to take these points and plug them into the third order polynomial, the p3 of x. And we had this before, but now the order has changed. So essentially the first point here will not be a of 0, it will be a of 2, which we know is f of 2 by definition. So in here we have f2 plus, and then here we have the x1, so that's going to be x minus x2 multiplied by the first divided difference between x1 and x2 plus then x minus x2, x minus x1 multiplied by the second divided difference, so x0, x1, x2, and then plus we should be having a third divided difference, but we haven't come up with it yet, so we need to formulate it. And for the time being, we're going to stick with this a notation. So remember, like before we had the a2, before we gave it some expression in terms of the divided difference, well, guess what? At the moment, we don't have an expression for the third divided difference, so I'm just going to write out the terms here. So we'll have x minus x0 multiplied by x minus x1 multiplied by x minus x2 multiplied by a3. And we're obviously interested in a3, and we're going to adopt the same process that we had before in order to figure out what it actually equals. So we're interpolating at a point x3, and we're essentially expressing f3 in terms of, well, all of this really, and we have to do something about it. But what can we do? What can we divide by? Well, we can first of all divide by x3 minus x2. Well, actually, I'm going to do something different first of all. So I'll take the f2 that we have here. I'll take the f2, I'll move it to the other side. So we'll have f3 essentially minus f2. And that's going to be lots of stuff. And then we're going to divide everything that's in here. So we're going to divide it by, we take the f3, so we take the third point. So when we talk about x, we're really plugging in x3 everywhere. So that's, you know, becoming x3 in all locations. And this is what's actually going to let us simplify this whole thing, because we're going to divide by x3 minus x2. Let me underline those points where this is actually present. So we're going to divide the whole thing on both sides by x3 minus x2. And what we get on the right is the following. We get the first divided difference between x1 and x2 plus x3 minus x1 multiplied by the second divided difference, x0, x1, x2, and plus x3 minus x0, x3 minus x1 times a3. So now you should probably recognize this part already, because this is the divided difference between 3 and 2. So we can rewrite this as the first divided difference, x2, x3. Okay, so we can continue simplifying this, because remember, eventually we want to come up with a3 somehow. So let's continue this arduous journey in attempting to simplify the whole thing. So essentially, first of all, I'm going to once again take this term and move it over to the other side. So we'll have the fx2, x3 minus fx1, x2, and all we're left with is this bit, this whole bit, and we want to get a3 from it somehow. And you'll notice that once again we have a common term that we want to divide by, and that's x3 minus x1. So if we rearrange the entire thing, we get something like the following. So we get x3 minus x0, a3 on the left. I'm just going to swap these things around, so we'll have x3 minus x0 multiplied by a3, and on the right hand side we have the following. So remember, we divided everything by x3 minus x0, actually x1 it should be, and here we have a divided difference between x2, x3 minus divided difference between x1, x2 minus the second divided difference, x1, x2, x3. There we go. So we're almost there. We're almost at an expression for a3, because essentially if you look up at this part, you can see that this particular thing, this entire construct, this thing, is the definition of the second divided difference. So I can effectively rewrite this as a second divided difference, x1, x2, x3, minus the second divided difference, x1, well actually no, that should be x0 here. So I think I copied them over incorrectly, x0, x1, and x2, and that would be x0, x1, and x2. And so we divide by x3 minus x0, so we can cross it over and put it here, x3 minus x0, and guess what? This is a3, and it happens to be the third divided difference. And it might not be obvious to you as to why this is so great, but in actual fact, if you look at each pair of the divided differences, you'll see that instead of solving any equations, all we have to do is plug in the values from the previous divided difference to get the next divided difference. So it's kind of like a triangle that folds on itself. So first of all, you have just the f values, and then you have the first divided differences, which fall to the second divided differences, and so on and so forth. And in the next clip, we'll actually take a look at some examples. Alright, you're now going to see just what makes divided differences so awesome. So let me just move this to the side a little bit, and we'll consider a very simple example. So let's actually let's make it another table of values. So I'll just have a few values actually. So let's have x with the values 1, 2, and 3, and have y, or f of x, with the values 6, 23, and 48, for example. So I'm going to go for a quadratic interpolation here, quadratic polynomials. So the way that we're going to lay out these examples is the following. So we'll have the function values and the x values first of all. So the x values will be 1, 2, and 3, and then the f values, the function values, would be, or indeed you could call them the polynomial values, because the polynomial has to go through these points, they will be 6, 23, and 48. And so after we've got these, we can calculate the first divided differences. And the divided differences are really easy, because what we're looking for in this particular location is the divided difference between x0 and x1, which is simply the distance between the values divided by the distance between the x's. So that's 23 minus 6 divided by 2 minus 1. So that's equal to 17. And similarly, we get the other one. So f x1 x0, and that's 48 minus 23 divided by 3 minus 2, and that's equal to 25. And then we get the second divided difference. So the second divided difference here, and that's the notation that we've used before, so that's f x0, x1, x2. But we know that the second divided difference can be expressed in pretty much this kind of fashion from the first divided difference. So once again, what we get here is 25 minus 17 divided by, and here is the tricky part, we divided by 3 minus 1. So we divided by the range, if you will, that these points apply to, because they touch 3 here and 1 here, and this gives you a value of 4. So essentially, if we want the polynomial, we've already got it. We've already got the polynomial, because what we're essentially now need to do is we collect this top diagonal and use these values in the formula which we already have for the polynomial. So the second degree polynomial of x is actually going to be 6 plus 17 times x minus 1 plus 4 times x minus 1, x minus 2, and that's it. And you can see where this comes from. So the 6 comes from here, the 17 comes from here, and the 4 comes from here. So after you multiply all of this out, you get 4x squared plus 5x minus 3. And that's the polynomial that we're looking for. Okay, now let's look at a more complicated example. So let's have a few more points here. So I'm going to have a bigger table, and we'll have x and f. And for the x values, we'll have 0, 2, 3, 5, 8, and 10. And here we'll have 1, 9, 43, 231, 993, and 1961. So once again, what we're going to do is we're going to build this kind of sideways tree, if you will, that narrows down to some point. So I'll move this here to the right so that we can draw the tree on the left. So let's have the x values first of all. That's once again 0, 2, 3, 5, 8. I should learn how to draw 8 and 10. And we'll have the f values as well, or the p of x values, if you will. That's 1, 9, 43, 231, 993, and 1961. Okay, so you take the first divided difference. So the first divided difference here would be 9 minus 1 divided by 2 minus 0, so that's 4. And I'm just going to fill in the other points briefly, so that's 34, that's 94, 254, and 484. Okay, and then you take the second divided difference. And the second divided difference, so 34 minus 4 divided by 3 minus 0, that's 30 divided by 3, so that's 10. And similarly, we have the other values, so that's 20, 32, and 46. And we can take the third divided difference, and that's going to be 2, 2, 2. So you can see these are all identical. And what this means is that there is no point in taking the fourth or the fifth divided difference, because we know that they're all going to be zeros. So essentially what we're after is a third degree polynomial. That's what will work for us. So we're essentially happy with this column. And what this means is we're going to take this set of values to build our polynomial. We'll take this set of values. So here is the third degree polynomial for our data set, P3 of x. And then we plug in those values, 1, 4, 10, and 2. So here we go. So that's 1 plus 4x plus 10x times x minus 2 plus 2x times x minus 2 times x minus 3. And this comes down to 2x cubed minus 4x and plus 1. And that's our polynomial. Alright, we're now going to talk about forward differences. So as you can imagine, if you open up a table full of values of statistical functions, you're going to see values which are equally spaced. So you would have, let's say you have the value of some function for 0.123, 0.124, 0.125. And once again, the question is, how do you find those in between values? Well, if the values are in fact equally spaced, in this case the difference is 0.001 in each of the values, then you can do a few simplifications to the difference and interpolation formulae. So we're assuming that there is some constant spacing between the x values. Let's call this h. So h is the distance between x0, x1, x2 and so on, and we have a fairly simple relevance formula for the relationship between h and x. So we can say that x at some index k is actually x at some index k minus 1 plus h, because h is the distance between each of these. Or if we're starting at x0, then xk is simply x0 plus k times h. Fairly obvious stuff. But now we're going to actually define something called a first forward difference. So let's write this down. First forward difference. Okay, so what is this first forward difference? Well, essentially, the first forward difference, which we'll define as delta fk, is simply the function at k plus 1 minus the function at k. It's probably worth illustrating at this point what we're talking about. So essentially, if you imagine a chart like so you have some function going like this, basically, then if we're taking two values, let's say the x at index k and x at index k plus 1, then if you look at the actual value of the function that this produces the value fk, and this produces the value fk plus 1. So the distance between these 2 points is called delta fk. That's the first forward difference. And then we can define the second forward difference. So the second forward difference is as follows. So that's going to be delta squared fk. So delta squared fk is defined as the difference between the deltas at k and k plus 1. So that's essentially delta f k plus 1 minus delta fk. And we can sort of go on with this and define the higher forward differences. So then we can apply our knowledge of divided differences that we have from before, and we can actually try to define those divided differences in terms of these forward differences that we have right here. So the first divided difference, so f with square brackets with x0 and x1, if you remember the definition of the first forward difference, it's essentially f1 minus f0 divided by x1 minus x0. However, we know that f1 minus f0 happens to be delta f1 by the definition of the first forward difference that we've introduced. So we can define it as delta f0 divided by h. And similarly for the second divided difference, so f with x0, x1, x2, that's going to be defined as a similar formula, but with the first divided differences plug in, and we're already taking these values and plugging them in. So that's going to be delta f1 divided by h minus delta f0 divided by h, all divided by 2h. And what we can do here is we can note the fact that delta f1 minus delta f0 happens to be the second forward difference, delta squared fk. So we can rewrite it. We can take the h and move it down. So this becomes 2h squared. And on the top we have delta squared f0 divided by 2h squared. And if you continue this idea, if you expand it to further divided differences, you'll get the following formula. You'll get the divided difference between x0 and a couple of points until some xn, being defined as delta to the power n f of 0 divided by n factorial times h to the power of n. So that's the formula that we are going to use, and we can formulate a new table. Remember when we were solving with divided differences, we had this table which was kind of like a converging triangle. We can define another one of those. So you can think of, once again, we'll talk about the x values. So you'll have the x values, x0, x1, x2, x3, and so on. And then you would have the function values, so f0, f1, f2, and f3. And then the f0 and f1 would become delta f0, delta f1, delta f2. And then you would have the delta squared f0, delta squared f0, delta squared f1, and then you'd have delta cubed f0, and that would be a corresponding table, similar to the tables that we had for divided difference. And what this is called is a forward difference table. Forward difference table. Okay, so what we're going to do now is a bit of a trick. We're going to do a change of variables so that instead of talking about discrete points like 0 and 1, remember we have to find the values between the points. So we can introduce some variable which will indicate how far we are in terms of h, because the distance between these 2 points is h, the distance between these 2 points is h, but we might want to get, for example, h over 2. So we're introducing a change of variables here. We're basically saying that we're going to define x as being equal to x0 plus some variable p multiplied by h, and p does not have to be a whole number. So essentially, if you want x1, then yes, you multiply h by 1, and you get effectively x1 equals x0 plus 1 multiplied by h. But our goal is to find those in-between values, and for that we would plug in smaller values of p, like for example the value of p equal to 1/2, meaning that if you have points x0 and x1, then setting p equal to 1/2 basically gives you the point that's actually in between these 2 points. That's what the whole procedure is all about. It's finding those values between the lines, so to speak, and then we can formulate the Newton's divided difference formula in terms of this new notation. So let's have a new formula. So we're looking at f at x0 plus p multiplied by h, which is equal to f of 0 plus p multiplied by delta f of 0 plus p times p minus 1 divided by 2 factorial delta squared f of 0 plus p times p minus 1 times p minus 2 divided by 3 factorial delta cubed f0, and so on. So this is our Newton's forward difference formula. Important concept, because we're going to use it in a moment. So let's take a look at an example. So here is a not so small example of some function. So let's actually have a few more values than we typically have. So I'm going to have a table of x values and a table of f of x values. Now in this case, I'm going to deliberately use a function which is quadratic, so that we're going to have a very nice formula. It doesn't always you don't always get the formula which matches the numbers exactly, but here we'll have some values of x. Let's have 0, 4, 8, 12, 16, 20, and 24, for example. And then we'll have values of f of x, so that's going to be 3, 59, 275, 651, 1187, 1883, and 2739. It doesn't really matter what they are, because we're really only interested in the top diagonal for the forward difference. So essentially, we want to find the first forward difference. First of all, remember we have this table. So the first deltas are actually easy, because they're just the differences between the f of x values. So you get something like 56, 216, 376, 536, 696, and 856. Okay, so that's easy, but the second differences are what we're really concerned with. So these are essentially all identical. They all have the same value. In this case, it's going to be the value of 160 in each one of them, which gives us an indication that we're matching perfectly with a quadratic polynomial of some kind. And we can formulate this polynomial and then use the formula, Newton's forward difference formula, this formula, we can use it to find some in-between values. So what kind of values do we want? Let's suppose that we want, for example, the value of the function f when x is equal to 2. Okay, so what do we know about the point 2? Well, we know it's right in between 0 and 4. So if this is x0, then this is essentially the x0, and p in this case is equal to 1/2. Remember, we agreed that p is a measure of the distance between the points. So p equals to 1 is a whole distance, given that all our points are equally distant from one another. So p equals to 1/2 is exactly the point that we want, x equals to 2. So what we do is we take the value of p equal to 1/2 and we simply plug it into the above formula. And we've already got these terms. We've got the delta f0, we've got delta squared f of 0. So essentially all we have to do is we take the value of p, we plug it here, here, here. We don't need the third order terms because on the second order we already have everything kind of matching, and we basically plug that in and get our values. So we calculate the function at x0 plus ph, and so we take these values, and essentially at the moment it's these sets of values. So we take first of all the f of 0, which is also this value 3, so we say 3 plus, then it's p times delta f of 0, so it's 1/2 times 56, so that's 1/2 times 56, and then the slightly more complicated p times p minus 1, so that's 1/2 multiplied by half minus 1 is minus 1/2, divided by 2 factorial multiplied by delta squared of f of 0, which happens to be 160, multiplied by 160, and the value that we get is 11. So that's the result for calculated at x equal 2. Okay, so let's try something else. Let's try a value which is further down the line. Let's suppose we want to calculate the function at x being equal to 11, for example. So 11 is somewhere down here. It's not exactly in the middle, but it's close. So what we're doing is, instead of taking these sets of values and setting p being equal to 1, 2, and 3/4, what we're doing is we're essentially just taking these values. We're taking the value starting at 8. So we're taking this set of values. Well, without the 8, obviously. We're taking this set of values and we're using that instead. So we're setting p equal to 3/4 because it's 3/4 distance from the 8 here. So we're essentially saying that in this case, the function at x equals 11 is equal to the following. So once again we take the 275. So we take this value 275 plus, and then it's p, which is 3/4 times 376 plus, and then it's 3/4 multiplied by minus 1/4 divided by 2 factorial and multiplied once again by 160, which gives us a value of 542. So this is how you apply Newton's forward difference formula. Lagrangian interpolation is a method of finding a polynomial which kind of fits your data. So let's take a look at what the typical setup is. So let's suppose that you have a bunch of observations. So you have, let's have a two-dimensional case with x and y coordinates. Let's suppose you have measurements for x being equal to 1, let's say 2, 3, and then 5, and you have some values corresponding to these measurements. So the idea here is that you want to construct some polynomial in order to approximate this set of data. And essentially what you want to do is, for example, you want to find out what is the value of y when x is equal to 4, for example. So how do you do that? Well, one of the ways this can be done is with polynomials, and essentially what happens is that you're attempting to have an approximation such as, well, a simple polynomial would be a line, just a linear kind of approach, or something more complicated like, let's say, a parabola going like this, or maybe a hyperbola going like this, or something else to that effect. So the idea is, how do we find the actual formula for all these polynomials? And for a number of points given, let's say, n+1 points, what we can do is we can try and formulate the interpolating polynomial in the so-called Lagrange form. So essentially what we're saying is that f of xi is equal to the sum from I going from 0 to n of y at this location times li, where li is that polynomial. And we'll see what it is in a second, because I'm going to rewrite it as the sum from I equals 0 to n of yi, and the polynomial itself is a product of the following. So it's a product of x minus xj divided by xi minus xj, where I is not equal to j, like so. So this may seem a bit cryptic, but we can now write out the polynomials for, let's say, 2 points. So let's say you have 2 points, x0 and y0, and x1, y1. What you can do is you can formulate this for 2 points, and it would look like this. So you would have f of x being equal to x minus x1 divided by x0 minus x1 y0 plus x minus x0 divided by x1 minus x0 y1. So the idea here is that if you have, let's draw the graph again. So if you have 2 points, so you have a point x comma y here, then the interpolating polynomial is just a line going through these 2 points. So it's going through x0, y0, and x1, y1 here, x1, y1, like so. Now for 3 points, it gets a bit more complicated, because we now have x0, y0, we have x1, y1, we have x2, y2. So there's going to be more terms in the addition. So essentially for this, the function of x is going to be x minus x1 divided by x minus x2 divided, that was a multiplication rather, than divided by x0 minus x1, x0 minus x2, y0, and then there's going to be another 2 terms, because then what happens is we have x minus x0 multiplied by x minus x2 divided by x1 minus x0, x1 minus x2, y1, plus, and then the third term. So the third term is x minus x0, x minus x1, sorry, that should be a 0 here, a 0 divided by x2 minus x0 multiplied by x2 minus x1, all multiplied by y2. So if we now draw the picture for this setup, we'll have something like the following. So essentially we have the point, this point xy, which lies on a line going through these 3 points. So essentially we have some sort of parabolic curve going like this, and then we know that this point is x2, y2, and some point here is x1, y1, and this will be x0, y0. Okay, so there is a general formula that you can use for interpolating this, for getting this set up, and it looks a bit convoluted. So let's try to write this out anyway. We essentially have a function represented as a large product, so that would be x minus x1 times x minus x2 all the way up to x minus xn divided by, and here we have x0 minus x1, x0 minus x2, and all the way up to x0 minus xn multiplied by y0 plus, and then you get the similar kind of thing for y1. So let me just write this out. So we have here x minus x0, so x minus x2 all the way up to x minus xn divided by x1 minus x0, x1 minus x2, and once again all the way up to x1 minus xn, y1 plus, and then there are lots of terms here, and essentially you get somewhere towards the end, and towards the end you get something like the following, and this is going to be a bit long, I admit, but essentially you get something like x minus x0 times x minus x1 all the way up to x minus xi minus 1. So getting close to the end of the whole thing, times x minus xi plus 1, and then all the way up to x minus xn. And this is all divided, should learn to draw straight lines, this is all divided by xi minus x0, xi minus x1, and then here we have xi minus xi minus 1, so 1 multiplied by xi minus xi plus 1. Oh, that should be a 1 again. Let me just edit it for clarity. So that's a 1, and multiplied all the way up to xi minus xn and times yi, and then the final term in this addition would be x minus x0 times x minus x1 all the way up to x minus xn minus 1 divided by xn minus x0, xn minus x1 all the way up to xn minus xn minus 1 times yn. So this rather convoluted formula is how you would go about taking a few values that you already have observed and actually getting a formula for them. So let's do a practical example of how you would do something like that. So let's suppose that we have a set of x and y values. So I'm going to just draw a simple listing. So I have x values of 0, 2, and 5, for example, and I'm going to have the y values of 1, 10, and 4. And what I want to do, for example, is I want to calculate the value of y given that x is equal to 10. So what is it? Now we're going to apply this formula up above, so let's do that. So essentially our function is going to be something like this. So we take these values and we plug them into the numerators and denominators. So we're going to have 10 minus 2 times 10 minus 5 divided by 0 minus 2, 0 minus 5 multiplied by the first y value, so that's a 1 times 1, then plus, and we have 10 minus 0 times 10 minus 5 divided by 2 minus 0, 2 minus 5, multiplied by the second y value, which is 10, and then the third term is 10 minus 0, 10 minus 2, divided by 5 minus 0, 5 minus 2, multiplied by the last value, which is 4, and what we end up with is 4 minus 83.33 plus 21.33, which is equal to minus 58. So there we have it. Without getting the actual polynomial written out, we already got our value, because essentially we took the 10 from here and we plugged it into the equation down below, and so we got our result. And now that we've looked at how this is done manually, let's actually jump into MATLAB and see how it's done there. Here is the implementation of Lagrangian interpolation in MATLAB. What you can see is that we're performing the summation of the different terms after each term is expressed as a product. So we essentially have the Li at each step being subsequently multiplied by each of the fractions. So effectively you can think of long fractions that we've written previously as fragmented into these separate xi minus xj over xi minus xj fractions, and then we keep multiplying them, excluding the condition when j is equal to I, and subsequently we perform a summation of all of these terms. So as a result, what we can do is we can take the data that we've just seen, plug it into this implementation, and see if we get the same result. So if you remember, we had x having the values 0, 2, and 5, and we had y with the values 1, 10, and 4, and we wanted to find out the value of y at x equals to 10. So let's do that. Lagrangian interpolation, provided the x, the y, and the value we're solving for, and as you can see, the result is minus 58, which is exactly what we had when we did it by hand. Lagrangian interpolation is very useful, but there is a problem with it, and that problem is fairly significant. The problem is that the error term in the Lagrangian interpolation is very difficult to apply, so the degree of the polynomial that's actually needed for a specific accuracy that you're after is generally not known until you've actually performed the computations. So a common practice, if you're interested in using the Lagrangian interpolation, is to compute the results given from various polynomials until an appropriate agreement with the actual function is obtained. However, the work done in calculating the approximation by the second degree polynomial, for example, does not lessen the work required to calculate the third approximation, nor is the fourth approximation easier to obtain than the third approximation, and so on. So Neville's algorithm is this idea of deriving these approximate polynomials in such a manner that uses the previous calculation to a greater advantage. So let's imagine that we have some function. Once again, we have a function f of x, which is defined at particular points. So those points would be x0, x1, x2, and all the way up to xn. And let's also suppose that we have a bunch of distinct integers. So let's call those m1, m2, m3, and so on up to some mk, where k is going to be the number of these distinct integers, and we're going to have a restriction that 0 is less than equal to mi less than equal to n, where n is the final index here for all indices I. Okay, so we have this restriction, and then what we can state is that the Lagrangian polynomial that actually happens to agree with the function f of x at these k points, which we'll call xm1, xm2, xm3, and all the way up to xmk. So the Lagrangian polynomial that actually happens to agree with this set of points, we're going to denote this polynomial as p with m1, m2, m3, and so on up to mk of x. So that's a fairly large looking index here. Okay, so let's take a look at an example. So, for example, let's suppose that we have the following values. Let's say we have x of 0 is equal to 1, and x of 1 is equal to 2, and x of 2 is equal to 3, x of 3 is equal to 4, and x of 4 is equal to 6. And the actual function that we're interested in, f of x, is equal to e to the power of x. So what we're going to do is we're going to try and first of all determine the interpolating polynomial. So that would be the polynomial at points, let's say 1, 2, and 4. So 1, 2, 4 of x. And we're going to use this polynomial to approximate the function at x equals 5. So this is the Lagrange polynomial. Let's actually write this down. So we're going to have this p1 to 4 of x being defined as follows. So we'll essentially, if we go the Lagrangian way, we'll have x minus 3 times x minus 6 divided by 2 minus 3, 2 minus 6, e squared, plus, and then the second part, so that would be x minus 2, x minus 6, divided by 3 minus 2, 3 minus 6. That would be e cubed, plus, and then x minus 2, x minus 3, divided by 6 minus 2, 6 minus 3, e to the power of 6. So essentially, if we want to find out the value of the function at x being equal to 5, then we can say that this is approximately equal to a polynomial fed the value of 5, so x being fed the value of 5. So we essentially take the value of 5 and we plug it into this whole thing above. And once we perform these calculations, we get something like the following. We get minus 1/2 e squared plus e cubed plus 1/2 e to the 6th, which is equal approximately to 218.1054. So that's our approximation. Now, the next result that we're going to look at, the theorem that we're going to look at right now, is basically describing a method for recursively generating the Lagrange polynomial approximations. So here is a theorem. All right, so let's suppose that we have some function f, and function f is defined on a certain number of points. So it's defined at x0, x1, and all the way up to some xk. And let's suppose that we have two distinct numbers somewhere in this set. We have two distinct numbers. Let's call them xi and xj. So then what we can say is that the polynomial approximation p of x can be defined as follows. So it's x minus xj of the polynomial, and here we're going to get a rather large subscript. So that's the polynomial which is affected by point 0, 1, then all the way up to j minus 1, then j plus 1, then all the way up to k. So that's a polynomial as a function of x, minus, and here we have x minus xi. So x minus xi of the polynomial where, once again, the indices go like 0, 1, and they go up to I minus 1, I plus 1, and all the way up to k. Once again, this is a function of x. And all of this is divided by xi minus xj. xi minus xj. Okay, so this theorem, it basically tells us that this polynomial that we've just come up with happens to be the kth Lagrange polynomial that interpolates the function f at k plus 1 points. So essentially, this is the kth Lagrange polynomial that interpolates the function f at k plus 1 points. So interpolates it at x0, x1, and all the way up to xk. So now we need to talk about the procedure that's actually used, that uses the result of this theorem to recursively generate the interpolating polynomial approximation. And this is what's actually called Neville's method. So Eric Harold Neville gave this, produced this modification for the Lagrange formula in a paper published in 1932. So here is the notation. We'll start with the notation first of all. Let me just see how we can move this around. There we go. Okay, so the schema goes something like this. So we're going to consider just a bunch of x values. So I'm going to have x0, x1, x2, x3, and x4. And for each of those, we'll have a polynomial, and we're still going to go with this notation of the full subscript. So we're going to have the subscript listing all the points at which the polynomial is kind of relevant. So we'll have p0 here, p1 here, p2, p3, and p4. And then what we can do as this sort of calculation progresses is these effectively get merged into p01. So that if you merge these two, you get p12. And then you can merge these and you get p012. And as you can imagine, as you keep merging them, you're going to get p0123. And eventually you get p01, 2, 3, and 4. You can pretty much guess what the other elements are. But the problem is that this p notation is really cumbersome because of the ridiculous number of subscripts that are being used to represent the actual entries. But you should note that it's really just an array that's being constructed, and you only need kind of the first and the last elements, and everything else is kind of obvious. So what we can do is we can reformulate this entire thing and kind of shorten the notation to avoid these multiple subscripts. So we're going to introduce a new letter. We're going to introduce a letter Q. So essentially the idea is that we're going to have Q with an index I and j of x, where i's and j's follow the following relation. So 0 is less than or equal to j, which is then less than or equal to I. And the idea is that if we're interpolating a polynomial of degree j, so this is the degree, then we're interpolating this polynomial, and the number of actual points that we have is j plus I. So we effectively, the points that we're considering are as follows. We have x at I minus j, then we have x I minus j plus 1, and all the way up to x I minus 1, and then xi. So the I and the j, they define the range of points that we're actually interested in, and that would correspond to this set of points, for example. So effectively what we're saying is we're saying that this Q notation with subscripts I and j is the same as the P notation, where it starts at I minus j and then goes to I minus j plus 1 and all the way up to I minus 1. and then I. And this should hopefully make it easier to represent the diagram that we've seen up above. Just rewrite it in terms of this Q notation. Let me scroll up just quickly. Okay, so once again we have our x0, x1, x2, x3, and so on, x4. And here we have, well, we have our P0. Well, the starting values are not so problematic. We have P0, P1, P2, P3, and P4. And in this case, if we adopt the Q notation, that's just Q0, comma 0. And for the other Qs, you're also going to have Q1, comma 0. So the second value is 0 because we don't really have a span from one value to another. It's just P1, and that ends up Q2, 0, Q3, 0, and so on. Okay, but this is where it gets interesting. So once these two are taken together, then you have P0, 1, which is represented as Q11. So essentially, it's a range which ends at 1 and has 1 element. That's all that we're saying, really. So once again, you merge these two, you get P12, and that is Q21. So it ends at 2, and it has well, a range of 1 between the elements, shall we say. That's one of the ways to phrase it. So eventually, as you kind of merge and merge and merge, you end up with that final value P0, 1, 2, 3, 4. And our notation is Q4, comma 4. So the last element is 4, and there is 4 additional elements to the left of it. That's how you can interpret the notation. So finally, we get to look at an example of how Neville's algorithm works. So let's actually get some numbers in here. So example. So let's suppose that we have a bunch of x and y values. Let's say we have x values of 0, 2, and 5. We have y values of 1, 10, and 4. And then this is our table. And what we want to find out is, let's say we want to find out the value of y when x is equal to 10. So how do we do it? Well, the q values at the left of the diagram are actually rather easy. So if we're looking at q0, 0 and q10, know that we already have these values because the zeroth order polynomial is just a constant. So we know that q of 0, 0 is equal to 1, and q of 1, 0 is equal to 10, and q of 2, 0 is equal to 4. However, for the other polynomials, we do actually have to perform some calculations. So for example, q 1, 1 is equal to, and this is going to be at the value of 10 here. So that's going to be x minus x0 multiplied by q10 minus x minus x1 of q0, 0, all divided by x1 minus x0. The x1 and x0 terminology is just another way of indexing these values. So we can plug the values in. We get 10 minus 0 times 10 minus 10 minus 2 times 1, all divided by 2 minus 0. So this gives us 46. And then q21 at 10, that can give us a value of minus 6. I'm going to skip the calculations here. And q of 2, comma 2 finally at the value of 10. That once again, this is where we incorporate the previous results. So maybe it's worth writing this out. So that's going to be x minus x0 of q2, comma 1 minus x minus x2 q1, comma 1 divided by x2 minus x0, and that's equal to 10 minus 0 times minus 6. see the minus 6 that we're taking from here, minus 10 minus 5 times 46, that's this value, all divided by 5 minus 0, and we get a value of minus 58. Okay, so here is the example of Neville's algorithm in MATLAB using the same data that we just had looked at and calculated by hand. So here is a set of x values, here is a set of function values at those points, and here is the point at which we actually want to calculate the entire thing. So what we're essentially doing is we're building an n by n matrix where the results, the values of those matrix are actually the intermediate calculations of the polynomial, and obviously the final, the sort of right-hand bottom value is the actual value that we're looking for. And as I run this, you'll see that the intermediate results that we're getting here, 46 and minus 6, are what we had previously for the second order, and it's a lower triangular matrix where the bottom right result is the value that we're actually looking for. So let's suppose that we're interested in a first derivative of a function. Now, we're making the assumption that we have the function to work with, meaning that we can plug any value of x and we can get the value of the function at that point x. What we don't have is we don't have any means of computing the first derivative, so we don't have some analytic solution for how to differentiate the function. Instead, we want to estimate the first derivative. So the definition of differentiation, if we remind ourselves of what this is, the definition is that df by dx is actually a limit with some delta x going to 0, of f of x plus delta x minus f of x divided by this delta x. So that's our formal definition. Now we can actually try using this formula to get different approximations of first derivatives, and there are actually different approaches to how we can go about it. So the first approach that we're going to take is called the forward difference. So the forward difference approximation is actually defined as follows. So we take df by dx at some point x being equal to xi, and we define it as the following. We say that we're going to take the function at xi plus 1, kind of the next point, subtract the current point fxi, and then divide everything by xi plus 1 minus xi. So what does this mean? Well, let's actually try drawing it. Let's draw just a very simple graph here. So this is the actual graph that we maybe want to find the derivative for. This is the actual point x for which we're trying to find the derivative. I'll call it xi, assuming that there are points to the either side. So xi is what we're interested in. Specifically, we're interested in the tangent, the slope, which might be something like this. So we're interested in this slope. However, since we don't have an analytic solution, we're not going to quite get this slope. Instead, what we're looking at is we're looking at other points. We're looking at xi minus 1 and xi plus 1. So we can sort of position them here, for example. And in the forward difference, we're only interested in xi plus 1. So here is some other point xi plus 1, and this point also happens to have a corresponding y value, obviously. So then what we're saying is that if this line is the true derivative of the point, the function at xi, then the approximate derivative is taken as follows. So we're essentially drawing a line from this point to this point, and we're saying that this is our approximation. So essentially what I can do here is I can draw this line. Well, it's not a very straight line, but you hopefully get the idea. So this line is our approximate first derivative. As you can see, the slopes are completely different. So it might not be the greatest of examples for this particular function because it's so curved. Now there is a point xi minus 1 here that we don't need for the forward difference, but we are going to need it for the backward difference. So the backward difference is actually very similar. So let's have backward difference. Okay, so the backward difference, I'm just going to go back into this function. So the backward difference actually takes the point at xi minus 1. So essentially the definition is very similar to what we had before. So df, let's do it like this. So df by dx calculated at x equals xi is actually taken as the following. Now here we took the current point and some point next to it, and we can do the reverse. So we can say that we're going to take the current point fxi, we're going to subtract the previous point f at xi minus 1, and we're going to divide once again by the difference in the x value. So that's xi minus 1. So essentially we're now saying that we're going to consider this particular point, this point here, and we're going to look at the slope, which goes like this. So it goes through these 2 points, like so. Okay, let me actually do the labels a bit better. So I'm going to wipe out this part, and instead let's have so this is the forward difference approximation, and this line is the backward difference approximation. Okay, so this is the two options, but there is another option, and the other option is called central difference. Central difference. So the central difference basically takes the previous point and the next point. So essentially its definition, I'm sure you've guessed it already, but let me just spell it out anyway. So df by dx at point x equals xi is estimated to be the slope between this point and this point. So in terms of our definition, that's fxi plus 1 minus f of xi minus 1, all divided by xi plus 1 minus xi minus 1. So once again, what we do, let me actually pick a different color here. Just a moment. I'm going to pick a different color, and we're going to draw yet another line, which is perhaps the best line of them all. So we're going to have a line that goes something like this. So this line is the central difference, and as you can see, it's pretty close in terms of slope to the true line. So here is the true line, and the central difference is getting pretty close. Now let's actually look at an example where we calculate these differences for a set of particular values, set of particular functions, and let's actually see what we get when we plug those in. So we're going to assume that we have the following function. So we're going to have a function f of x being equal to 3x squared. Okay, and we want to evaluate f prime of x at a point x equals 2. So we want to calculate the first derivative at x equals 2. So we do know analytically that the first derivative of the function is actually 6x. So the value of derivative at x is equal to 2 is actually equal to 12. But we're going to ignore that for now, because we're essentially going to do numeric differentiation as opposed to analytic differentiation. So first of all, we need the values of f of x. So we're going to since we're calculating it at x equals 2, I'm going to take the values of x of 1, 2, and 3 for our backward difference and forward difference and central difference approximations, and then I'm going to calculate the function f of x for all of them. So it's going to be our little table of values. So f of 1 is equal to 3, f of 2 is equal to 12, f of 3 is equal to 27. Okay, so now we can calculate those finite difference approximations. So first of all, let's do the forward difference. So with the forward difference, we're essentially calculating f of 3 minus f of 2 divided by 3 minus 2, and that's equal to 15. So that's not quite the same as 12. In fact, if we calculate the error, So the error is actually equal to 15 minus 12 divided by 12. So that's 3 over 12. So that's essentially 25%. So we got a 25% error. Now let's do the backwards difference. So second option is backwards difference. Once again, we do f of 2 minus f of 1 divided by 2 minus 1. And that's equal to 12 minus 3 divided by 1, which is equal to 9. So 9, once again, is not the same as 12. And if we calculate the error, we get 9 minus 12 divided by 12 modulus. So that's once again a 25% error. So in both the final difference and the backward difference, we're actually getting quite a significant error. Obviously, if we moved the points, if we move the points 1 and 3 closer to the value of 2, we might get better results. But for this example, we're not going to do that. We're going to consider the central difference next. So finally, let's do the central difference. So the central difference is where we take the 1 and the 3. We take the edge values. So we get f of 3 minus f of 1 divided by 3 minus 1. So that's 27 minus 3 divided by 2. And that's 24 divided by 2, which is 12. And our error is equal to 0 because that happens to be the correct result. So once again, the results show that the central difference actually gives us a more accurate estimate. When we talked about first derivative approximations, we essentially had either backwards or forwards or central differences around a point xi. So we had a point at which we wanted to evaluate first derivative, and then we looked at another point to the left of it, sort of xi minus 1, and another point to the right of it, xi plus 1. We're going to continue with this theme, but now we're going to talk about second derivative approximations. So essentially we have the formula, in fact, a 3-point central difference formula for second derivatives. So a second derivative at a point x can be approximated with the following. We can approximate it as f of x I minus 1 minus 2 f of xi plus f of x I plus 1, like so, all divided by delta x squared. Remember, delta x is once again the distance between these points. So it's really delta x here, and similarly delta x here. Here we're squaring delta x. So this is our formula, and we can now try applying it to estimate certain second derivatives. So let's imagine that we have a function defined as follows. Let's have a function 3 to the power of x divided by 3x. Okay, so we can certainly, let's suppose we want to find out the derivative, the second derivative at a point x equals 3. Now, first of all, what I can do is I can just tell you what the actual value is, because we can get an analytic solution. In this particular case, we can just differentiate the function twice and apply the x equals 3. So I can tell you that the analytic solution is somewhere around 2.0903. But we're going to do it using the approximation method, the approximation formula that's described here. So once again, to get the f of xi values, we need to calculate them basically. So we have x values. I'm going to, if we're going to calculate this at x equals 3, what I'm going to do is I'm going to decide that delta x is going to be 0.3. So essentially, we already have the value at xi, that's the 3, that's the value we want to calculate. And then xi minus 1 is going to be 3 minus the delta, so that's 2.7. And similarly, we're going to have xi plus 1, that's going to be 3 plus the delta, so that's 3.3. Okay, so we want to have these values calculated for us. So that's going to be the actual x values are going to be 2.7, 3 and 3.3. And if we calculate the function at these particular points, we're going to get something like the following. We're going to get 2.3974, 3, and 3.792. So armed with this data, what we can do is we can plug these values into this formula here, and we can try and calculate the second derivative. So essentially, the second derivative here, just to illustrate how to plug in all these values. So the second derivative at 3 is actually equal to the function at 2.7 minus 2 times the function at 3 plus the function at 3.3, all divided by delta x squared. So that's 0.3 squared. And we already have these values. So this value goes in here, this value goes in here, and this value obviously goes in here, and we plug those in, and the value we get is something like 2.1042. So you can see that it's reasonably close to this value. It's not exactly the same. And we can actually calculate the error. So in this case, the error is equal to 2.1042 minus 2.0903 divided by 2.0903. So that's equal to 0.665%. So actually pretty good. So the results, these results, they basically show that the 3-point central difference formula gives a very accurate approximation for the value of the second derivative. Let's talk about the error terms that we get from Taylor series expansions, because we have several formulae for approximating the derivative at some point xi. So typically when we're interested in this derivative, we look at equally spaced points around xi. So you might have xi minus 1 here, xi plus 1 here, and you might have more points, but we're mainly concerned with kind of forward differences, backwards differences, and central differences. So the Taylor series expansion works fine in the case where these points are equally spaced. And we're going to consider a 2-point forward difference formula for the first derivative. So we're interested in a function f evaluated at a point xi plus 1 based on the knowledge of xi. So we can use the Taylor series and we can describe it as f of xi plus the first derivative of xi times h plus the second derivative of xi divided by 2 factorial times h squared, and so on. You can pretty much guess what the terms are, or not so much guess as you should be able to tell what they are from the Taylor series. So in this case, I'm using h, which is simply the increment, the distance between the points. So that would be essentially xi plus 1 minus xi. Okay, so we have this formula, and what we can also do, the way that we can rewrite this formula is by using the remainders of the Taylor series. So if we were to rewrite this in terms of the remainder of the Taylor series, kind of ignoring the higher order terms and just leaving a remainder in place, we'll get something like the following. So we'll get f of xi plus 1 being equal to f of xi plus the first derivative at xi times h plus the second derivative at some value xi divided by 2 factorial h squared. Okay, and what we're interested in, at the moment at least, is the first derivative. So we're essentially interested in this part. So we can rewrite this entire thing in terms of the first derivative. We can say that the first derivative at a point xi is actually the function at xi plus 1 minus the function at xi divided by h, and then minus this term, so minus the second derivative at xi divided by 2 factorial h. And notice it's h, not h squared, because we lost one of the h's as we were dividing. Okay, so what this tells us is that we now have an approximation for the first derivative, and this thing on the right hand side happens to be the error term. So this is essentially the truncation error or the discretization error. Let's just call it DE for short, discretization error. So this is kind of the extra part that we would actually be ignoring typically if we were discarding the higher order terms. So essentially what we can say is that this discretization error is on the order of h because that's the multiplier here. H is the multiplier to this entire thing, and it basically tells us that the smaller the H value, obviously the smaller the overall error is. So this is what it looks like for a forward difference. We can do a similar calculation for the backward difference, and we'll still come up with roughly the same result. In fact, the only real difference is that you would have something like the following. So you would have the first derivative at xi minus 1, xi minus 1 being defined as f of xi minus the first derivative of xi h plus the second derivative, once again at xi, divided by 2 factorial h squared. And once again, you go ahead and you solve for the first derivative. And in this case, the discretization error is once again on the order of h. So there is a question is whether we can actually improve upon this. So to improve upon this, we'll call upon the central difference, because that's something that's a bit more exciting. So essentially, let's rewrite, once again, let's rewrite the final differences, but have a few more terms, and we're also going to have different psi values for the kind of things that we're going to be looking at. So let's do this. So once again, just a reminder of what the formula are. So for the forward difference, we have f of xi plus 1 being equal to f of xi plus first derivative at xi times h plus the second derivative at xi divided by 2 factorial, sorry, this should be a 2 factorial h squared plus, let's have some remainder here. So the third derivative of some value xi1, not very good at drawing these, so this is going to be xi with index 1 divided by 3 factorial multiplied by h cubed. So the idea here is that xi1, which I'll try drawing as neatly as I can, is somewhere between xi and xi plus 1. Okay, and now we're going to have the other side, sort of the backward difference. So essentially we'll have xi minus 1 being defined as f of xi minus the first derivative at xi times h plus this term, then minus this term. The only difference is that when we talk about the kind of final term, the one where the remainder is, we're going to have a different xi value. So maybe we'll have xi2, so xi with index 2. And if xi with index 1 is between xi and xi plus 1, then similarly xi with index 2 is something that's going to be between xi minus 1 and xi. That's the only difference, but apart from that, it's really all the same. So we're going to have h cubed here. Okay, so we have two representations, and for the central difference, what we essentially get is we can actually kind of integrate both of them together. So we can take both of them together, and we'll come up with something like the following. So if you think of, because what we're really interested in is obviously the first derivative, once again, this part, but we cannot just add these two formulas together, because then the plus and the minus will kind of consume each other, and that's not going to be a very nice thing. So essentially we want to perform a subtraction. So let's try doing a subtraction instead. So we're going to subtract this from this, kind of like this, and we're going to have f of xi plus 1 minus f of xi minus 1. Sorry, that minus 1 is actually an index, so it should be a bit lower, xi minus 1 here. And that's going to be basically f of xi minus f of xi. Those disappear. And then the first derivative minus minus gives us plus, so that becomes a 2 first derivatives at xi h, and then we add up this term minus this term. So essentially we have the third derivative at xi1 h cubed over 3 factorial, and then another plus because this minus and this minus gives a plus, so another minus for the third derivative of xi2 divided by 3 factorial h cubed. Okay, so now we've done it in such a way that we can in fact go ahead and extract the first derivative, because that's what we're interested in right now. So the first derivative at a point xi is going to be defined as f of xi plus 1 minus f of xi minus 1, like so, divided by 2h, plus these terms. Now remember, we're to get rid of this h, we're dividing by h, so we're going to have h squared here and h squared here. So once again, we can just say that this is h squared. So what we essentially come up with is the fact that for the central difference gives an approximation which is more accurate because the error term, the discretization error, is actually of a higher order, and that's always a good thing. Now we can just briefly look at the second derivative. So I'm just going to write out the formula for the second derivative. So f of xi plus 1, we'll do the forward first of all. So that's f of xi plus the first derivative of xi times h plus the second derivative of xi divided by 2 factorial h squared plus the third derivative. We'll have the third derivative of xi divided by 3 factorial h cubed plus the fourth derivative f4 of, once again, we're going to have xi1 divided by 4 factorial of h to the 4, and we'll have a similar formula for xi minus 1. So it's just that the sign, some of the signs here will be negative, so there's going to be a minus here, and there's going to be, well, that's actually not correct. No, there's going to be a minus at this location. There's going to be a minus at this location, I believe. So apart from that, it's going to be almost identical, except that here on the final kind of term, we'll have f4 of xi2 divided by 4 factorial h to the 4. But apart from that, it's all more or less equivalent. Now, what we can do in this case, because we're not interested in the first derivative, we're actually interested in the second derivative, which is this part. What we can do is we can actually add them up. And if we were to add them up, we'll get something like the following. So we'll have f of xi plus 1 plus f of xi minus 1. And that's going to be equal to, so f of xi and f of xi, that's 2f of xi. The pluses and the minuses kind of cancel themselves, but we do get the second derivative. So we get two second derivatives of xi divided by 2 factorial times h squared. And then we have these two terms. So these two terms, they just, they go as they are, so we add them up, and that's where they will be. So once again, if you were to solve for the second derivative, so for this part, because that's what we're interested in, you'll get something like the following. So you have the second derivative at a point xi, which is equal to f of xi minus 1 minus 2f of xi plus f of xi plus 1, all divided by h squared plus, and this is the important part, order of h squared. So once again, we're getting the error term on the order of h squared, just to explain how this came to be. These are h to the 4 here. However, to get rid of this h squared here, we essentially divide everything by it, and that explains the h squared here, the fact that the second derivative has been extracted without the h squared. So on the right we have h to the 4, both divided by h squared, and this is why we get this kind of error term. So this basically once again shows that the central differences for the second derivative are pretty good, because they give us an O of h squared error term. We're now going to talk about something called Richardson's interpolation, and this is a technique that's used to actually generate high accuracy results while using low order formulas. So you can imagine us, for example, using the forward difference method for a first derivative, but then improving on it using Richardson's interpolation. However, to explain how it works, this is going to take a bit of time, so I'm going to take it slow and let's see how we get on. So essentially, remember that we're typically, when we interpolate something, we typically have a step size. So we can define that step size as delta x or just simply h. So this is the step size. We assume that for each of the step sizes, we have some approximation formula. So as you choose a particular step size for the algorithm that you're working with, you essentially have some formula. Let's call it n1 of h. So you actually have an approximation formula that's parameterized by the delta. So essentially, the smaller you make your subdivisions, for example, in the case of integration, the better the result, obviously. So we always want to have a smaller value of h as possible. So essentially, we have n1 of h, and this is approximating some constant m. Let's assume that we know what the result actually is. Now, since this is likely to be some sort of iterative procedure, we have truncation error. So we can express a truncation error in the following form. So we take the actual result, and then we subtract what we got as the estimate, n1h. And we can actually rewrite this as a sum of power series. If we think of a certain number of coefficients, let's say we have coefficients k1, k2, and so on, we can rewrite this as k1 times h plus k2 times h squared plus k3 times h cubed, and so on. So we don't know what these constants are yet, but we're just making the assumption that it's possible to actually formulate the truncation error in terms of these constants. Okay, so we know that the truncation error is on the order of h. So unless there is a very large variation in the k constants, of course. So essentially what we can do then is we can make the following statements. We can say that m minus n of 0.1, for example, is approximately equal to 0.1 k1. And we can similarly say that m minus n of 0.01 is approximately equal to the order, so it's 0.01 k1, and so on. And in general, we can say that m minus n, n1, let's not forget the index here, n1 of h, is approximately equal to k1 times h. Okay, so I've ignored the other terms here because obviously they are much smaller than the first term. So you can make this kind of argument essentially. So now our goal is to find an easy way to combine all these rather inaccurate approximations. So we have a bunch of approximations which are all O of h, so on the order of the subdivision that we're actually making, and we want to combine these approximations in a way so as to produce formula with a higher order truncation error. So we don't want a truncation error on the order of h, we want it on the order of, let's say, h cubed or something like that. So how do we do it? Well, let's suppose that we can combine different n1 of h formulas to produce a truncation error on the order of h squared, for example. So that is actually our goal. Let's suppose that we have a new formula. Instead of n1 of h, we actually have n2 of h, and we say that the actual value minus n2 of h, and let's suppose that we can now represent this without this k1 of h term, because now the error is on the order of h squared, so we can start with that. We can say that there is some k2, let's have them with a hat. So k2 h squared plus k3, once again with a hat, h cubed, and so on. So this is much better because the error is obviously much smaller. It's on a higher order, h squared here. So once again, we have a bunch of these unknown constants, k2 hat, k3 hat, and so on. And similarly, if we were to plug in actual values, we can say that, for example, m minus n2 of 0.1 is equal to, and here is a surprise, it's 0.01 times k2 with a hat. And similarly, if you had, let's say, m minus n2 of 0.01, then this 0.01 will get squared, and you'll get something like 0.0001 times k2 with a hat as well. So if these constants, k1, the k1 here and the k2 with hat here, if these two constants are of roughly the same magnitude, then we can say that the n2 approximations are much better than the corresponding n1 approximations. So this interpretation can actually continue by combining the n2 approximations in a manner that produces the formulas with the order of h cubed, h to the fourth, and so on. So we can take it almost to infinity. So to see specifically how we can generate the interpolation formulas, let's consider the O of h formula for approximating the m. So let's suppose that, let's get back to this idea that m is represented as our approximation formula n1 of h plus the error stuff. So that's k1h plus k2 h squared plus k3 h cubed, and so on. So this formula is assumed to hold for all positive values of h. So we can actually replace the parameter h by half its value, for example. And then we have a second O of h approximation. So we have something like the following: m equals n1, and now we do h over 2, plus k1 h over 2 plus k2 h over 4 plus k3 h over 8, and so on. So what we can do is we can actually take this particular line and we can subtract it from the line above, and we can actually subtract it from twice the equation above to attempt to eliminate the term that actually has the k1 in it. So the goal here is that we take all of this. So I'm gonna actually number them. So if this is 1 and this is 2, so what we want to calculate is 2 times this equation minus the previous equation. So once you write that out, you end up with the following. You end up with m being defined as n1 of h over 2 plus, and here in brackets we have n1 of h over 2 minus n1 of h plus k2 h squared over 2 minus h squared plus k3 of h to the cubed over 4 minus h cubed, and so on. So essentially what we do is we define n2 as the following. We say that n2, if we just continue this idea, we define n2 as n1 of h over 2 plus n1 of h over 2 minus n1 of h. So that's essentially this first part, and we kind of throw away the higher order terms here. So the equation of a higher order for m is an OH of squared approximation. So essentially we have m now being equal to n2 of h minus k2 over 2 h squared minus, well, if you really must have the other terms, minus 3k 3 over 4 h cubed, and so on. So essentially we have an order of h squared approximation, which is what we wanted in the first place. So now that we've done all this writing out, let's actually look at a practical example. So remember that when we talked about the forward difference method with a step of 1, so we had h equal to 1, or we called it delta x, but we can call it h. So when we have we had this method with this step equal to 1, what we were trying to do is we had the function f of x being equal to 3x squared, and we wanted to find out the first derivative at a value x equals 2. Now we know that the value is actually 12 from analytics. So let's assume that this original formula, the original forward difference formula, has a error term of order of h. And then we're going to use Richardson's interpolation on these values to see if we can actually get a better approximation. So in the previous example, we found that when we had h equals 1, that gave us the second derivative at a point of 2, having the value of 15. So that was quite far away from the actual value of 12. If we now take h to be, let's say, 1/2, and we actually calculate this in MATLAB, you'll find that the first derivative at a point x equals 2 has the value 13.5, like so. So basically this implies that n1 of 1, remember the h gets plugged into the n1, has the value 15. And it also implies that n1 of 0.5, a finer approximation, has the value 13.5. And we have n1 of 1, we have n1 of 0.5, and this is something that we can now use in our formulas above. So we're going to define n2. So n2 of 1 is going to be defined as n1 of 0.5 plus n1 of 0.5 minus n1 of 1. Okay, so we can try plugging in these values, and what we're actually going to get is, surprisingly enough, the value of 12. And go ahead and plug in these values if you don't believe me. So essentially, this gives us a much better value, because the error, if we look at the errors in both of these, there is a 25% error for this one. There is a 12.5% error for this result, which is better, but still not great. And for this result, the error happens to be 0. We get exactly the result that we want. So essentially what this shows once again is that Richardson's interpolation gives us a more accurate approximation. We have finally reached the section on numerical integration, the so-called quadrature. So what is quadrature? What is it all about? And why do we care about numerical integration? Well, in actual fact, I would argue that numerical integration is actually more important than differentiation, because the problem in both cases is, what if you have a super complicated function? How do you differentiate and integrate it? But in the case of differentiation, you can, in many cases, get away with, even if a function is complicated, you just use a combination of the product rule, the quotient rule, the function of function rules, and eventually you arrive at some analytic solution where you can just plug in the value. But in contrast to that, the integration process, sometimes you don't even have an indefinite integral. So for example, if you have something like the integral of, let's say, the square root of sine of x. square root of sine of x dx. That's not something that you can find an analytic solution for, or similarly something like 1 over the square root of 1 plus x cubed, for example. So these are the kinds of integrals where it makes sense to go looking for a numeric solution. But also sometimes you do get integrals which you may as well integrate analytically. So for example, you might have an integral of 1 over 1 plus x cubed, but if you actually look at what the solution is like, if you actually use MATLAB or something to evaluate it, you'll see that it's really a horrible, really long expression just to take this one simple integral. So that is not exactly easy to calculate either, and that's why we turn to all sorts of numerical methods and to the quadrature process. So the quadrature process is actually it's better than numeric differentiation in terms of the rounding errors, and it's possible to obtain very accurate approximations. They're only really limited by the computer that you're using, or the calculator in this case. So once again, the quadrature is actually based on the idea of approximating the integrand by a polynomial of some low degree, and this is then followed by integrating the polynomial to obtain an approximate value for the integral. And so in this section, we'll basically be talking about approximation of integrals using mainly linear and quadratic functions. The trapezium rule is one of the simpler rules of quadrature, so let's take a look at how that is defined. Essentially, what we're trying to do, as always, is we're trying to find the numeric value of some integral. So essentially, we have some function maybe going like this, and we want to find an integral between 2 points a and b. Let's mark them like so. And what we do is we subdivide the integral into several strips. So what we're basically saying is we're going to evenly divide the range between a and b into several strips, and then we're going to evaluate the strips using some simplified procedure. So the trapezium rule is probably the simplest procedure there is, actually. So once you arrive at the subdivisions, what you do essentially is you connect the endpoints. So you say, let's just connect the function points and evaluate the areas of the trapezium. So you connect these 2 points and these 2 points and these 2 points and these 2 points, and you take each of the trapezium, you calculate the area, and you simply add them up. That's all there is to it. So essentially what we're doing as a kind of approximation of the integral is we're saying that some integral going from x at index k to x at index k plus 1 is actually being estimated as the area of the trapezium, which is h over 2, where h is this distance, so we'll call it h, and it's this distance over 2 multiplied by the sum of the function values, so it's f at k plus f at k plus 1, because that's the formula for the area of a trapezium. So essentially what we can do, and I'm not going to show it here, but we can show that the error in calculating the trapezium compared to a function, for example, is somewhere on the order of the following: minus h cubed multiplied by the second derivative of the function at some point c divided by 12, where c is between those 2 points. So c is between some 2 points xk and xk plus 1. So this is the error estimate for a single trapezium whose area is being calculated. Of course, we want to sum several of them up. So what we're essentially saying is that the integral going from a to b of some function f of x dx is actually a sum of these little integrals, so a sum from x0 to x1 of the integral plus the sum from x1 to x2 of, once again, that same integral, and all the way up to the sum, or the integral of xn minus 1 to xn f of x dx, assuming that we're subdividing everything into n separate strips. So essentially we can rewrite this in terms of our estimates using the trapezium rule. So we have this formula with h over 2 here, h over 2 of the two function values on either side. So we can essentially say that this is h over 2 of f0 plus f1 plus h over 2 f1 plus f2, and so on all the way up to h over 2 fn minus 1 plus fn. So essentially what we can do with this is we can rewrite it, because you'll notice that some of the terms are duplicated here. So you have f1 here, f1 here, you have f2 here and f2 here, and all the way up to fn minus 1, which will be here and here, but there's only one f0, there's only one f of n. So essentially all those two terms, when they divided by 2, they just left with h, so we may as well divide f0 and fn by 2 as well. So this all simplifies to the following. So you multiply h by f0 over 2 plus f1 plus f2 and all the way up to fn minus 1 plus fn over 2. So that's the trapezium rule with the application of the actual formula, and we can also estimate the error similarly. So the error is based on the error that we have for the individual strip, the error that I've mentioned here. And essentially, let's just write this down. I'm not going to do the workings for the error. So the error here is minus b minus a multiplied by the multiplied actually first of all by the distance between the points squared multiplied by h squared, then times the second derivative at some point c divided by 12, where c is somewhere between a and b. So that's our error term. Let's take a look at an example of actually applying this procedure to evaluate some integral. So we're going to calculate a reasonably simple integral, the integral of, well, let's have 1 over x. So let's have an example. Okay, and what we're trying to do is we're trying to calculate the integral of 1 over x dx from, let's say, 1.3 to 1.4, and we're actually going to not even consider subdivision. We're just going to consider the points 1.3 and 1.4, meaning that, you know, if you have a function going like this, then all you're doing is, instead of evaluating the actual area under the curve here, you're basically drawing a trapezium like this, and you're calculating the area of the trapezium, and you're saying, well, this is an estimate of some kind. So let's see how it goes for this particular approach. So what we're essentially saying is that we're taking the value of h to be equal to 0.1. That's the distance between the left point and the right point, between 1.3 and 1.4. So we have the h value, which is 0.1, and then we apply the formula that we had up above here. So essentially we say that, oh, let's just divide it by 2 and multiply it by the sum of the functions at those points. So we plug in 1.3 in here, we plug in 1.4 here, we get 1 over 1.3 plus 1 over 1.4, and we get the value of 0.07418. Okay, so we can also calculate the error, because we can take the derivative. So the first derivative of x is equal to minus 1 over x squared, and the second derivative of the function is equal to 2 over x cubed. So essentially we can basically plug in the second derivative in here and calculate those values. So the error, let's just calculate the error. Error is going to be equal to minus, and then b minus a is minus, well, it's 0.1, but it's also multiplied by h squared, which is also 0.1 squared. So that's 0.1 times 0.1 squared, that's 0.1 cubed. And then it's divided by 12, and then we have 2 over c cubed. And let me explain where this comes from. Because on top we have the second derivative at c, but the second derivative is actually 2 over x cubed. So essentially it's this term that's being kind of replicated here with the value of c replacing the value of x. And of course we have this requirement that c is somewhere between a and b. So in our case, c is somewhere between 1.3 and 1.4. If we want to maximize the error, if we want the maximum value, then we have to take c being equal to 1.3, in which case the error is going to be equal to somewhere around 8 by 10 to the minus 5. So if we now calculate the integral using something like MATLAB, for example, so if we actually get the value of the integral to within some precision, let's say 5 decimal places, we would get 0.07411. So if you look at the estimate that we got, which is this value, and if you look at the actual value, you'll see that the difference is actually 7 by 10 to the minus 5, whereas our estimate is 8 by 10 to the minus 5, so it's a pretty good estimate of the actual error. When it comes to numeric integration, there are typically obvious choices of how to actually calculate the estimate, the approximate integral. So you're interested once again in some integral going from a to b of some function f of x dx, and you want to get it numerically. So if we were to actually draw some function, so let's draw a function looking kind of like this, and let's suppose that this is a and this is b. What you can do in order to estimate the integral is you can subdivide this area, because what we're essentially interested in is this area under the curve from here to roughly here. So in order to get some approximate value, what you can do is you can subdivide. You can say that we're going to subdivide the range from a to b into 4 strips. So I'm going to subdivide it into 4 separate strips like so. Now, in order to be able to estimate the integral, we have to decide how we want to treat these strips. And typically we want to treat them as rectangles, because calculating the area of a rectangle is rather simple, and we don't have to deal with the curvature of the function or anything. Of course, it doesn't give us an exact value, but it gives us a value that's good enough. So under the midpoint rule, the midpoint rule basically says the following: that once you made the subdivision, how about we take the midpoint of each of the strips across the x-axis? So we take this point, this point, this point, and this point. And what we do then is we actually evaluate the function at this point. So we grab this point, we look at what the function actually is. So the function will be obviously at this point, and then we treat this strip as a rectangle, which obviously has the width, let's call the width dx, delta x rather. So this is going to be the width of the strip, and the height of the strip is going to be treated as this value, and this value happens to be f at, well, let's call it f at xi, where I is the index of the actual strip center. So essentially we're taking this rectangle that I'm drawing in white, and we're getting its area. We're getting the area of this. Then we do the same for the next strip. So once again, we take the midpoint, we evaluate the function, which we turn it into a rectangle, and once again evaluate this area, and we continue until we run out of strips. So essentially the width of each strip, like for example the width of this strip, we can say is delta x times f at xi. Or if we want to actually use the terms for a and b, we can sort of formalize this a bit further, in the sense that we can, for example, say that the estimate of the integral, the approximate integral, is actually a sum. Now remember, each of the strips is delta x wide, so we can put the delta x here. Now by delta x, obviously we mean that given we made a subdivision of n strips, delta x is actually defined as obviously b minus a divided by n, because the overall range is b minus a, and we have n strips here, so it's b minus n divided by a. So then we take the sum, and to sum we need to calculate the actual values at the midpoints. So that's essentially using our function. So that's going to be a function at a particular point, and we can certainly just call it xi and be done with it. But in actual fact, this midpoint here is a, well, first of all, we start on the left, so it's always a plus, and then if we give it an index, let's say I going from 0 to n minus 1, I'm starting with 0 because I want to have the vanishing part if going from the left. So that's going to be a plus, and then we take as many delta x's as there are indices. So we say I times delta x, and then we also take another half of the range. So we essentially take another delta x over 2, or we could sort of we could group these together if we wanted to. So this formula essentially allows us to estimate the approximate integral based on these midpoints of the strips that we've created. Now let's take a look at how this is done in MATLAB. Okay, so here is the implementation of the midpoint rule in MATLAB. It's actually very simple. So we have a function called midpoint rule, and it takes 4 arguments. The first argument is the function that we're actually integrating. The second 2 arguments are the limits of the integration, and the final argument is the number of strips that we want to subdivide the range into for purposes of estimation of the integral. So first of all, we calculate the delta x. That's just the difference between the integration limits divided by the number of strips that we want to make. And now that we have the width of the particular strip, we calculate the value of the function at this strip. But to do that, we need the actual x-coordinates. So to find those x-coordinates, the coordinates of the midpoints, what we're essentially doing is we're saying that we're going to start at a point a plus delta x over 2. So that's the first midpoint. And then we go up until the last midpoint. And the number of midpoints is obviously the same as the number of strips. So that's the value of n. So now that we collect the x-coordinates of each of the midpoints at which we're evaluating the function, we simply say y equals f of xi, and that gives us essentially a vector of y values, and all we have to do is add up those values together and multiply them by delta x. So let's take a look at how this actually works in practice. So I'm going to call the midpoint rule. We'll take a function like the cosine, and we're going to evaluate it from 0 to, let's say, pi over 2, and I'm going to start with 10 strips. So if I evaluate this, I get 1.001. So this is very close because we know that the actual value is 1 exactly. We've actually overshot the value by just a little bit. So if we increase the number of strips to 100, for example, you'll see that we're getting more precision now. We're getting 1.000, and then we get some error, an error here, and as we keep increasing it to, let's say, 1,000, we're getting even better. So essentially this basically shows that as you increase the number of strips, then obviously you're getting a more accurate result. We're now going to talk about something called the Gauss-Hermite quadrature, and this quadrature actually relies on the so-called Hermite polynomials. So that's what we should probably start with. So the Hermite polynomials, they actually they're defined using a recursion formula. So the first polynomial h0 of x is defined as 1. Not very exciting, I know. The second polynomial h1 of x is simply 2x, which is also not very exciting. However, from then on, they follow a recursion relationship. So we say that h with index n of x is actually defined as follows. So that's 2x times h n minus 1 of x minus 2 times n minus 1 multiplied by h n minus 2 of x. So these are Hermite polynomials, and they're actually used as weights in an approximation of the Gauss-Hermite quadrature. So essentially, what we're trying to do is we're trying to approximate the following integral. So we're trying to approximate an integral going from minus infinity to infinity of e to the minus x squared times f of x dx. All right, so we're trying to approximate this integral using obviously n points. And the approximation that we're doing is the following. We're saying that this is roughly equal to a sum, and this sum goes from 1 to n, where n is the number of points that you've chosen. And the sum, what's under the sum, is a weight at index I multiplied by the function at x with index I, depending on how you've actually separated this particular range, what your choice of n actually is. So the question is, well, what about this weight? What is this weight? How is it defined? And in actual fact, this weight is defined through the Hermite polynomials that we see above. So let's write down this definition. So essentially, the weight with index I is defined as follows. It's actually 2 to the power of n minus 1 times n factorial multiplied by the square root of pi divided by n squared multiplied by the Hermite polynomial squared. So the Hermite polynomial at n minus 1, no less, of x with index I all squared. So these are the weights. We'll see them later on when we actually write this whole thing in MATLAB. So essentially, this is a procedure for, this is a procedure that's essentially going to be used in connection with normal random variables. And you can sort of see it by the fact that we have, e to the minus x squared here. That should be a hint. So essentially what we're trying to do is we're trying to approximate, we're trying to essentially get an expectation, because if you look at what this is, or what this looks like, it looks like an expectation. It's something times a function. So essentially, given that we have, let's say we have a random variable called y, which is normally distributed with mean mu and standard deviation sigma, for example, then what we can say is that the expected value of some function which actually takes y, so the expected value of some function y, can then be defined as the following. It's 1 over sigma times the square root of 2 pi multiplied by the integral from minus infinity to infinity of the exponent of minus, and here comes the fraction, so it's minus y minus the mean squared divided by 2 sigma squared times f of y dy. Okay, and we're essentially trying to get it into this form, and we've got this form. So what can we do? Well, in actual fact, what we can do is a linear change of variables. So we can say there's going to be a new variable, let's call it x, and x is going to be defined as y minus the mean divided by square root of 2 sigma. And after we adopt this approach, we get a different kind of expectation. We get a different expression for the expectation. Specifically, we get an expectation which can be rewritten in terms of the sum, just like what we have above. So essentially, we can rewrite this as follows. So essentially, this is going to be 1 over the square root of pi multiplied by the sum going from I equals 1 to n of the weights, so wi, times the function at the following value. So it's at root 2 sigma xi plus mu. There we go. I've omitted the working that is required to understand what this is, but I'm just giving it out here as a result. So essentially, the wi here are the weights of the Gauss-Hermite quadrature, and the xi are the actual nodes over the range from minus infinity to infinity that we're actually concerned with. Okay, so let's take a look at an example, kind of a practical example. So let's suppose that you are an investor. You hold a bond. Let's say you hold a bond which is worth 1, and you also have some equity. So you have equity, and the equity has some value z, for example. And we're going to assume that z is log normally distributed. In other words, we're going to assume that log z is normally distributed with mean mu and standard deviation sigma. And what we're trying to figure out is what would happen when the owner of this portfolio actually decides to liquidate it at some future. I mean, what is the utility function this portfolio has? And indeed, we can formulate the utility function as follows. So we can say that u is actually 1 over sigma times root of 2 pi multiplied by the integral from minus infinity to infinity of the exponent of minus x minus mu squared, should be familiar, times 2 sigma squared multiplied by the function of 1 plus e to the x dx. So that's what we're trying to find out. And we actually have this property, that the property of log nominal distribution, in fact, that the expected value of e to the x, where x has this distribution, is in fact the exponent of the mean plus 1/2 of standard deviation squared. So let's take a look at how this can be calculated in MATLAB. Alright, so here is a demo in MATLAB, and I'm going to slowly go through what's going on here and explain how we're calculating it. So we're taking different values of n. We're looking at n equal to 2, 3, 4, 7, 13, and we're trying to see what the error is effectively, because we know the true value. We can get the true value from the formula I've just shown. So the true value is 1 plus the exponent of mu plus half sigma squared, and we can also predefine our own mean and our own variance as well, or standard deviation, and we can actually compare the calculated values, the values that Gauss-Hermite gives us, against the values which we know to be true. So here is the Gauss-Hermite implementation itself. It's actually done in terms of MATLAB functions, so we're not explicitly calculating Hermite polynomials and whatever. Instead, we define the function. We use the function for the Hermite polynomial. We actually use a numeric solver, and we simply evaluate this value and put it into the appropriate storage location, so x in this case. And similarly, we calculate the weights, but in the case of weights, yes, this is where we perform the calculation according to the formula that I've shown at the beginning of the clip, and we once again use the Hermite h function, which actually calculates the polynomial. So essentially what happens is we calculate the Gauss-Hermite values, so x and w as well. We plug the x value into the reverse transform, if you will. So we get the value of y. Remember, we did a transform, so now we're kind of doing a reverse transform, and then we simply do a dot product of the weights and 1 plus the exponent of the reverse transform values divided by square root of pi, and that's our approximation basically. And then what we're saying is we're comparing the true value with the approximate value, and we're looking at the relative difference. And here are some of the results that we're getting. So you can see that we're calculating it with the values of n of 2, 3, 4, up to 13, and we're seeing the error slowly disappear. So with 2 values, we have the error as roughly 2/10,000, and then it goes to 10 to the minus 6, and eventually to 10 to the minus 16. So it's a pretty good estimate for a numeric procedure. The Gauss-Laguerre quadrature is used in order to estimate a particular integral, and this time round we're interested in the following integral. We're interested in an integral going from 0 to infinity of e to the minus x times f of x dx. So we want to get this integral, and this integral is also going to involve a certain kind of polynomial. In this case, what we need is Laguerre polynomials. So the polynomials are once again defined in a recursive relationship. So the L0 of x is defined as 1. The L1 of x is defined as 1 minus x. However, the recursive relationship is rather complicated. So L with index n of x is defined as follows. So it's a fraction, and on top we have 2n minus 1 minus x times L n minus 1 of x minus n minus 1 times L n minus 2 of x. And this is all divided by n. So this is the Laguerre polynomial, and we're going to use it when we come to actually estimating this integral, because essentially the definition of the Gauss-Laguerre approximation is as follows. So the integral from 0 to infinity of e to the minus x f of x dx is taken to be approximately equal to the following sum. So we have a sum going from 1 to n of some weight at index I, like so, multiplied by f at xi. Okay, and this w is the weighting, and the weighting is actually defined as follows. So w at I is defined once again as a fraction. It's got xi on top, and on the bottom it has n plus 1 squared multiplied by the Laguerre polynomial at xi squared. So the Laguerre polynomial at n plus 1, note, of xi squared, like so. All right, so maybe we don't want to have just a polynomial where we have e to the minus x. Maybe we're interested in a more complicated integral. For example, we might be interested in an integral starting at some limit value a, going to infinity of e to the minus r times, I'm going to use y here because we're going to do a change of variables in just a moment. So we might be interested in this polynomial. So integral from a to infinity, e to the minus ry f of y dy. So in this case, what we can do once again is we can do a linear change of variables. So we can say that x is actually going to be r times y minus a, in which case we can rewrite the integral. So we can say that this integral is actually going to be equal to e to the minus RA divided by R multiplied by the sum going from 1 to n of Wi times f of xi divided by R plus A. So the usefulness of this is that we can evaluate certain integrals which are, well, some of them are well known. Like, for example, if you take the gamma function. So the gamma function, the gamma of some parameter alpha is defined as follows. It's defined as an integral going from 0 to infinity of e to the minus x times x to the power of alpha minus 1 dx. So this approach allows us to evaluate these kinds of integrals much faster. Now, let's actually take a look at how this is done in MATLAB. Here is an illustration of the Gauss-Laguerre procedure in MATLAB, and what's happening here is fairly simple. So we're comparing the approximate values that we're getting through the Gauss-Laguerre quadrature with the supposedly true value that we get from calculating it with the gamma function that's built into MATLAB. Of course, you have to bear in mind that gamma function is by definition a numeric procedure, therefore MATLAB itself also has its own tolerance values for how precise it is. However, it's better than what we'll be getting because we're approximating it using polynomials. So essentially what's happening here is we're specifying certain numbers of the sets of polynomials that we're actually interested in using to evaluate this thing. So we're saying let's evaluate it with 5, 10, 15, or 20 such elements. And then what we're doing is we've predefined some value of alpha. It doesn't really matter what it is. And we're going through each of the n's and actually calculating the Gauss-Laguerre parts. So here is the function which does the Gauss-Laguerre. Essentially, what's happening here is we're getting the actual values. That's done by getting the Laguerre polynomials using the Laguerre L function and then using VPA solve, which is a numeric solver, to get the actual values. And similarly, we're getting the weights as well. So the weights follow the formula that we've outlined previously. So we simply once again reuse the Laguerre polynomial here, and we end up with sets of x values, what we had as x subscript I values in the handwritten part of this demo, and we have the sets of weights. And then what we can do after we've got these weights is we'll simply do a dot product between the weight and x to the power of alpha minus 1, and thereby we have our approximate values. So we can compare the true value to the approximate value, and you can see some of the results here. So the results are not as spectacular as with some of the other polynomial approaches in terms of the error, but we're still getting fairly reasonable values here, and you can see that the size of the error is going down as we're increasing the number, the actual value of n.